You step onto the surface of an alien world only to realize, within seconds, that your body was never meant to be there. Maybe the air itself burns your lungs, or the crushing pressure turns you into pulp. Perhaps the cold is so intense that your cells shatter, or the gravity is so weak that a single step sends you spiraling into the void. The universe offers an endless variety of ways for you to meet your demise. The different planets and moons present unique and horrifying challenges that make the dangers on Earth look tame. In this journey through the most hostile places in existence, we'll explore the science of dying on different worlds and, just as intriguingly, what it might take to cheat death in the most extreme environments the cosmos has to offer. Mercury's solar furnace, perishing in extreme radiation. Mercury, the closest planet to the Sun, exists in a realm of extremes. Unlike Earth, which enjoys the protection of a thick atmosphere and a powerful magnetic field, Mercury is almost completely exposed to the Sun's unrelenting energy. Here, solar radiation dominates, making it one of the most hostile environments in the solar system. Every moment, the planet is bombarded by intense ultraviolet radiation, X-rays, and high-energy particles, all streaming directly from the Sun. With no thick atmosphere to filter or scatter this energy, Mercury's surface absorbs nearly all of it, transforming the planet into a blistering inferno by day and a frozen wasteland by night. The Sun looms 3 times larger in Mercury's sky than it does on Earth, and the radiation it delivers is up to 7 times more intense. At this distance, sunlight is not just visible light, it carries ultraviolet rays powerful enough to break apart molecules and X-rays that can strip electrons from atoms. The planet's proximity to the Sun means it also faces the full force of the solar wind, a constant stream of charged particles traveling at hundreds of kilometers per second. These particles slam into Mercury's surface, eroding material and even creating a thin ghostly exosphere, a tenuous layer of atoms that are continuously knocked free from the planet's crust by radiation. During the day, temperatures on Mercury's surface soar to 430 degrees Celsius, or about 800 degrees Fahrenheit. This is hot enough to melt lead, and it happens because Mercury lacks an atmosphere thick enough to redistribute heat. Unlike Earth, where air molecules scatter and absorb sunlight, softening its impact, Mercury's thin exosphere does almost nothing to reduce the Sun's intensity. Every photon of light that reaches Mercury's surface strikes with full force, heating the ground to extraordinary temperatures. But even this extreme heat is not the most dangerous aspect of Mercury's solar exposure. The planet is constantly bombarded by X-rays and ultraviolet radiation that would be instantly lethal to any form of life. These high-energy waves penetrate deep into surface materials, changing their composition over time. The relentless radiation gradually darkens the surface, breaking apart molecular bonds and creating a landscape that has been reshaped at the atomic level. Unlike Earth's surface, where wind, water, and tectonic activity constantly refresh the landscape, Mercury's surface is largely unchanged, except for the effects of radiation and meteorite impacts. Occasionally, the Sun unleashes solar flares, violent eruptions of radiation that send waves of energy into space. Even more extreme are coronal mass ejections, which launch billions of tons of charged particles outward at immense speeds. When these storms reach Mercury, they deliver an intense blast of radiation, temporarily increasing the planet's exposure to deadly particles. While Earth's magnetic field deflects much of this energy, Mercury's weak magnetic field offers little protection. The result is a world where radiation levels can spike without warning, creating an environment that is as unpredictable as it is dangerous. The constant bombardment of high-energy particles contributes to the creation of Mercury's exosphere, a layer of atoms that surrounds the planet. Unlike Earth's thick atmosphere, Mercury's exosphere is so thin that individual particles rarely collide. It is constantly being replenished by radiation striking the surface and knocking atoms loose. Sodium, potassium, oxygen, and other elements drift away from the planet, creating a shimmering halo that glows faintly in the sunlight. But this exosphere does nothing to shield Mercury from radiation. Instead, it is a product of the relentless energy that sculpts the planet's environment. Exploring Mercury presents immense challenges due to its exposure to radiation. Spacecraft sent to study the planet must be designed to withstand both intense heat and constant bombardment from high-energy particles. Electronics must be heavily shielded, as unprotected components would quickly degrade under the relentless radiation. Solar panels, which spacecraft rely on for power, face rapid wear from ultraviolet exposure, requiring special coatings to extend their lifespan. Even spacecraft orbits must be carefully planned to minimize the time spent in the most hazardous regions. If humans were ever to set foot on Mercury, the challenges would be even greater. A person standing on the surface without protection would receive a lethal dose of radiation within hours. Any potential outpost would require extreme shielding, possibly by building underground or using thick, radiation-resistant materials. The heat would make it nearly impossible to work during the day, while the lack of an atmosphere would expose astronauts to the full force of micrometeoroid impacts and cosmic rays. Every rock, every grain of dust on Mercury's surface has been altered by billions of years of exposure to radiation. The planet is a living record of the Sun's influence, a place where solar energy shapes the very fabric of the landscape. Venus's acidic agonies, succumbing to a corrosive inferno. Venus, though similar in size and composition to Earth, is anything but Earth-like. Instead, it is a place of relentless heat, crushing pressure, and an atmosphere so toxic that it destroys almost anything that dares to enter. If Mercury is a world shaped by the Sun's brutal radiation, Venus is a world ruled by chemistry, a planet where corrosive acids fill the sky, and the air itself is a lethal poison. The first challenge of Venus is its dense, suffocating atmosphere. Made mostly of carbon dioxide, this thick layer of gas traps heat with incredible efficiency, creating a greenhouse effect far beyond anything seen on Earth. Sunlight passes through the clouds and heats the surface, but instead of escaping back into space, the heat is trapped beneath the heavy atmosphere. As a result, Venus is the hottest planet in the solar system, with surface temperatures that reach 475 degrees Celsius, or about 900 degrees Fahrenheit. This is hotter than Mercury, despite Venus being nearly twice as far from the Sun. Floating high above the planet's surface is a thick layer of clouds, but these are not like the water clouds on Earth. Instead, they are made of sulfuric acid, a highly corrosive substance that burns through most materials on contact. These acid clouds stretch across the entire planet, forming a thick yellowish haze that completely hides the surface from view. Sunlight struggles to penetrate this dense atmosphere, scattering and refracting as it moves through layers of toxic gas. The corrosive power of Venus's atmosphere makes it a nightmare for exploration. Sulfuric acid is one of the most reactive substances known, capable of dissolving metals, eating away at rock, and destroying electronic components in minutes. Any spacecraft that attempts to descend through the atmosphere must be prepared for an onslaught of chemical attacks. Protective coatings can delay the inevitable, but nothing lasts forever in this environment. Even the most durable materials degrade quickly, their surfaces etched and corroded by the acidic rain. However, the acid does not reach the surface. Venus is so hot that any sulfuric acid droplets falling toward the ground evaporate before they land. Instead of acid rain, Venus experiences a never-ending cycle of acid mist, droplets that condense, fall, and then vaporize before completing their journey. This toxic cycle continuously replenishes the planet's thick cloud layers, ensuring that the sky remains a permanent swirling mass of corrosive fumes. As if the acid weren't enough, Venus's atmosphere is also filled with carbon monoxide, chlorine, and other toxic gases. The air is so thick that standing on Venus would feel like being 3,000 feet underwater on Earth. The pressure is nearly 90 times greater than Earth's atmospheric pressure at sea level, more than enough to crush most objects. Any lander or probe must be built like a submarine, designed to withstand the immense forces pressing in from all sides. The Soviet Union's Venera missions were the first to experience Venus's brutal environment firsthand. In the 1970s and 1980s, several Venera landers managed to reach the surface, but none lasted long. The first ones were crushed before they even touched down. Later landers survived the descent but functioned for only a short time before succumbing to the heat and corrosive atmosphere. Even the most advanced models lasted no more than 2 hours before their instruments failed. Their metal components weakened, their circuits overheated, and their protective coatings eroded under the relentless assault of Venus's toxic environment. The thick, carbon dioxide-rich air is dense enough to slow down meteorites before they hit the ground, reducing the number of impact craters compared to other rocky planets. The surface itself is covered in vast plains of hardened lava, evidence of past volcanic activity. Some scientists believe Venus may still be volcanically active, with eruptions releasing more sulfur dioxide into the atmosphere and maintaining the planet's acidic clouds. Some researchers have speculated that certain layers of Venus's atmosphere, high above the surface where temperatures are cooler, might be able to support microbial life. On Earth, some bacteria can survive in highly acidic environments, leading scientists to wonder if similar organisms could exist in Venus's upper clouds. However, the overwhelming acidity and lack of liquid water make this an unlikely scenario. The extreme temperatures make it nearly impossible for traditional spacecraft to operate on the surface. Electronics fail in the intense heat, and materials degrade rapidly under the pressure and corrosive conditions. Any future missions to Venus will require entirely new technologies, such as heat-resistant electronics, advanced cooling systems, and specially designed materials that can withstand prolonged exposure to acid. Martian dust and radiation, the slow asphyxiation on the red planet. Mars is often called Earth's sister planet, a world that once held water and may have supported the conditions for life. The first and most immediate threat on Mars is its atmosphere, or rather, its lack of one. The air on Mars is thin, more than 100 times less dense than Earth's atmosphere. It is made almost entirely of carbon dioxide, with only trace amounts of oxygen. A person standing on the surface without protection would suffocate in seconds. There is no air to breathe, no pressure to keep the body functioning. The blood would begin to boil in the low-pressure environment, leading to unconsciousness and death almost immediately. Even if someone had an oxygen supply, the problem wouldn't end there. The thin atmosphere is so ineffective at trapping heat that temperatures can drop to -73 degrees Celsius or 100 degrees Fahrenheit at night, causing a slow and relentless freeze. Solar radiation bombards the surface constantly, passing through the thin atmosphere with little resistance. Over time, exposure to this radiation increases the risk of cancer, weakens the body, and damages cells beyond repair. Any human living on Mars would need constant shielding, either underground or inside specially designed shelters. Even with protective suits, long-term exposure would have irreversible effects. The radiation does not kill instantly. It works slowly, eroding the body from within, making survival a race against time. The dust on Mars presents an equally insidious challenge. Unlike dust on Earth, which is soft and worn down by moisture and wind, Martian dust is sharp, dry, and electrostatically charged. It clings to everything, coating surfaces, clogging machinery, and damaging electronics. The dust is so fine that it seeps into every crack and opening, wearing down seals, filters, and mechanical parts. It can disrupt electrical systems, block solar panels, and interfere with vital equipment. In an environment where every system must work perfectly for survival, the slow accumulation of dust can be deadly. Breathing Martian dust would be even more dangerous. The fine particles contain toxic compounds, including perchlorates, chemicals that are harmful to human tissue. If inhaled, this dust could damage the lungs, causing severe irritation, inflammation, and long-term respiratory issues. Unlike a sudden disaster, exposure to Martian dust would be a gradual but unstoppable problem, weakening the body with every breath. Over time, it would lead to lung disease, infections, and eventually, a slow suffocation. Mars is also home to some of the largest dust storms in the solar system. These storms can engulf the entire planet, darkening the skies for weeks or even months. During these storms, sunlight is blocked, cutting off power to solar panels and plunging the planet into an extended period of cold and darkness. Temperatures drop even further, and visibility is reduced to almost nothing. Unlike the fierce storms on Earth, Martian dust storms are not deadly because of their wind speed. Due to the thin atmosphere, even strong winds would feel like little more than a gentle push. The real danger comes from the dust itself, which remains suspended in the air, coating everything in a fine layer of abrasive material and reducing visibility to near zero. The Moon's silent void, expiring in a vacuum of isolation. The Moon is the closest celestial body to Earth, a barren and lifeless world locked in silence. From its surface, the sky remains black even under the sun's harsh light. There is no air, no weather, and no sound. Unlike Mars, where dust storms creep across the landscape, or Venus, where clouds of acid swirl in an oppressive atmosphere, the Moon offers nothing at all, only a void, empty and unforgiving. Exposure to the Moon's vacuum would be immediate and absolute. There is no buffer, no protective layer of gases to slow the process. The moment a person is exposed, the air in their lungs is forced out, leaving nothing behind. Any attempt to hold a breath would be fatal, as the expanding gases in the body would rupture lung tissue in an instant. Within seconds, the lack of oxygen causes unconsciousness. The heart would continue beating for a short time, but without pressure to contain bodily fluids, water in the blood would begin to vaporize, causing swelling and internal damage. The human body, held together by internal pressure on Earth, begins to break down when that pressure is removed. The absence of an atmosphere means there is no protection from the sun's radiation. The illuminated side of the Moon reaches temperatures hot enough to boil water, while the dark side plunges to freezing extremes. Without air to conduct heat, the only way for objects to warm or cool is through direct exposure or radiation. A human caught in the sunlight would feel heat seeping in slowly, burning exposed skin without the protection of an atmosphere to diffuse it. In the shadows, the cold would steal warmth just as effectively, draining energy until freezing set in. The Moon's gravity, only 1/6 of Earth's, offers no comfort. While it allows for easier movement, it also creates a slow and eerie fall when objects drop. Without an atmosphere to create resistance, there is no wind, no rustling of fabric, no sound at all. The only noises that exist are those carried through solid objects, the vibrations within a spacesuit or a habitat. The silence of the Moon is absolute, broken only by the mechanical hum of life support systems. There is no erosion, no weather to alter the surface, no cycle of life. It is a place where time seems frozen, where the only evidence of activity is the marks left by past missions. Even the footprints of astronauts from decades ago remain undisturbed, preserved in the same condition as when they were made. A single puncture in a spacesuit or a small breach in a habitat could lead to catastrophic depressurization. The air would rush out violently, dragging anything unsecured with it. In a matter of moments, the safe interior would become as uninhabitable as the surface outside. Unlike a fire or a flood, where survival depends on fighting against the elements, a vacuum leaves no room for struggle. Once the air is gone, there is nothing left to resist. Io's volcanic fury, a fiery end amidst eruptions. Io is the most volcanically active world in the solar system, a tortured landscape that never stops changing. Unlike Earth, where volcanoes exist in specific regions, Io's entire surface is a battlefield of fire and molten rock. It is a world in constant turmoil, reshaped daily by eruptions, lava flows, and geysers of toxic gas. Io's surface is covered with hundreds of active volcanoes, some of which are the most powerful in the solar system. Unlike the volcanoes on Earth, which erupt sporadically and remain dormant for years, the volcanoes on Io are constantly spewing lava, reshaping the landscape in real time. The sheer scale of these eruptions is unlike anything seen on Earth. Plumes of molten rock and sulfur dioxide gas can rise hundreds of miles above the surface, reaching into space before falling back down as frozen particles. Some volcanic fountains on Io launch material so high that it escapes the Moon's weak gravity entirely, becoming part of Jupiter's vast magnetosphere. The lava on Io is far hotter than anything found on Earth. Some flows reach temperatures of over 1,300 degrees Celsius, hot enough to melt steel and vaporize rock. Rivers of molten rock carve deep channels into the surface, spreading out for miles in all directions. On Earth, volcanic activity eventually cools and hardens into solid ground, but Io's lava fields are constantly being replaced by new eruptions. The ground beneath a person's feet could crack open without warning, releasing fresh magma and turning a once solid surface into a river of fire. The gravitational forces that power this volcanic activity come from Io's constant struggle between Jupiter and its neighboring moons. Io is caught in a gravitational tug-of-war, stretched and compressed as it orbits its giant parent planet. This constant flexing generates heat deep inside the Moon, fueling its volcanic eruptions. Unlike Earth, where internal heat comes from radioactive decay, Io's energy comes from the brute force of gravitational interactions. The result is a world where fire and molten rock are the norm, a place where eruptions never truly stop. The landscape of Io is a chaotic mix of lava plains, towering mountains, and vast fields of frozen sulfur. The sulfur ejected by eruptions blankets the surface in shades of yellow, orange, and red. Some areas are coated in black volcanic rock where fresh lava has cooled just enough to harden before the next eruption takes place. Craters dot the landscape, but unlike those on the Moon, these craters are not the result of asteroid impacts. Instead, they are massive volcanic depressions, the remnants of past eruptions that have drained underground magma chambers. Sulfur compounds dominate Io's surface, making it one of the most chemically hostile places in the solar system. The thin atmosphere, composed mostly of sulfur dioxide, offers no protection from space and no air to breathe. Unlike Venus, where the thick clouds create a crushing pressure, Io's atmosphere is barely present. It is thick enough to be hazardous, but too thin to provide any meaningful cover from the vacuum of space. Sulfur dioxide is highly toxic. On Earth, it is known as a major pollutant, a gas that causes respiratory problems and acid rain. On Io, it exists in massive quantities, released continuously by volcanic eruptions. A person standing on Io would be exposed to a mix of freezing temperatures, scorching lava, and a toxic atmosphere. Even if they had an oxygen supply, breathing in any of Io's air would cause severe lung damage. The gas would react with moisture in the body, turning into acid and burning tissue from the inside. The temperatures on Io vary wildly depending on location. Near an active lava flow, the heat is intense enough to cause instant burns, melting anything unprotected. But just a short distance away, where the ground is not being heated by volcanic activity, temperatures can drop to minus 168 degrees Celsius or minus 270 degrees Fahrenheit. Without an atmosphere to distribute heat, there is no middle ground. Either a person would be incinerated near an eruption or frozen in the cold of space. Io's volcanic eruptions also create deadly electrical storms. When sulfur and rock particles are ejected into space, they interact with Jupiter's powerful magnetic field. This generates immense electrical currents, creating lightning storms far more powerful than anything seen on Earth. These energy discharges are strong enough to fry electronics, disrupt communication, and potentially kill anything exposed to them. The instability of Io's surface makes it impossible to predict where the next eruption will occur. Even if a person were to find temporary safety on solid ground, that safety would be short-lived. Lava flows can travel at high speeds, covering miles of terrain in a matter of hours. Unlike Earth, where people can study a volcano and predict its behavior, Io's eruptions follow no predictable pattern. The entire Moon is one massive, unpredictable volcanic system, shifting and changing on a scale far beyond anything on Earth. Europa's frozen oceans, dying beneath an icy veil. Europa is a frozen moon orbiting Jupiter, with an ocean hidden beneath its thick outer shell. Unlike Io, where fire dominates the surface, Europa is a place of cold, crushing pressure and treacherous terrain. At first glance, it may seem lifeless and still, a frozen wasteland locked in perpetual winter. But beneath the unbroken ice stirs a vast ocean, deeper than any on Earth, sloshing in the darkness, held in place by the unrelenting force of the ice above. The ice covering Europa is a barrier, miles thick, locking in the ocean below with an unyielding grip. Temperatures on the surface rarely rise above -160 degrees Celsius or -260 degrees Fahrenheit. Anything exposed to this brutal cold would freeze solid within moments. Both flesh and metal would become brittle in the extreme conditions. Europa's ice is jagged and broken, shaped by tidal forces from Jupiter's immense gravity. The Moon is constantly stretched and compressed as it orbits the gas giant, causing the ice to crack and shift. These forces create deep fractures known as lineae, long scars that run across the surface like veins, marking the places where the ice has broken apart and refrozen. Some of these fractures may still be active, grinding together as Europa flexes under Jupiter's pull. Anyone traveling across this terrain would face an unpredictable landscape of fissures and shifting ice, where the ground itself can open up without warning. The most immediate danger on Europa is the possibility of falling through one of these cracks. Some fissures expose layers of slushy, partially melted ice, where the crust is weak and unstable. A single misstep could send a person plunging into the frozen abyss, trapped beneath tons of unyielding ice. The cold would sap heat instantly, making escape nearly impossible. Even if someone could fight their way to the surface, the extreme cold would freeze any exposed moisture in seconds, turning breath to frost and limbs to stone. Water from the ocean below may be forced upward through the cracks, erupting onto the surface in plumes of freezing vapor. These plumes can rise miles into space before falling back down as frozen particles. Anyone caught in such an eruption would face a violent blast of supercooled water, capable of encasing them in ice almost instantly. Even spacecraft or equipment in orbit would need to be wary, as these plumes could coat surfaces in frost or interfere with delicate instruments. But the real terror of Europa lies below. Beneath the ice, an ocean stretches across the entire Moon, deeper than anything found on Earth. This water, kept liquid by the gravitational forces that knead Europa's interior, is a vast, alien sea, untouched by sunlight and hidden in perpetual darkness. No one knows exactly how deep it goes, but estimates suggest it could be more than 60 miles deep, nearly 10 times deeper than Earth's Mariana Trench. The weight of all that water creates immense pressure. The deeper one goes, the more crushing the force becomes, far beyond what any human body could endure. At extreme depths, the pressure is enough to collapse submarines and crush anything caught in its grasp. A person unlucky enough to be dragged into the depths would not survive long. Even if they had protection against the cold, the sheer weight of the water above would squeeze the life out of them, breaking bones and crushing lungs with relentless force. Without sunlight, the water is pitch black, a world where sight is useless and sound is swallowed by the abyss. Navigation would be nearly impossible, with no clear way to tell up from down. The frigid waters would drain heat rapidly, making hypothermia a constant threat. If something were to go wrong, if a suit were to tear, a vehicle were to fail, or an opening in the ice were to seal shut, there would be no way back. The frozen ceiling above would become a trap, sealing anything beneath it in a watery grave. Europa's ocean may also contain powerful currents, shaped by the same tidal forces that fracture the ice above. These currents could sweep anything away, pulling it deeper into the unknown, making escape even less likely. There is no solid ground to anchor to, no stable point of reference. In these waters, survival depends on technology, and any failure would mean certain death. Titan's methane seas, drowning in alien hydrocarbons. Saturn's moon. Titan is a world of thick orange haze, a place where rivers flow, lakes ripple, and seas stretch toward the horizon. But this is not Earth. The rivers do not carry water. Instead, Titan's surface is carved by liquid methane and ethane, hydrocarbons that would be gases on Earth but remain liquid in Titan's freezing climate. The Moon's thick atmosphere hides an alien landscape of strange chemistry. The sky is filled with a thick, smog-like mist that filters out the sun. The air is dense, thicker than Earth's, pressing in with a weighty stillness. A person could walk freely without needing a pressure suit, but that freedom would be an illusion. Titan's air is almost entirely nitrogen, with no oxygen to breathe. Worse, the atmosphere is laced with methane, an odorless gas that displaces breathable air and suffocates anything relying on oxygen. Within minutes, a person would lose consciousness, their lungs filling with gas that cannot support life. The surface temperature hovers around -179 degrees Celsius or -290 degrees Fahrenheit. Any exposed skin would crystallize almost instantly. While Titan's atmosphere is thick, providing more air resistance than Earth's, it is not stable. Methane exists in all three phases, solid, liquid, and gas, creating a bizarre cycle similar to Earth's water cycle. Methane rain falls from Titan's thick clouds, freezing cold and chemically toxic. The most unique danger on Titan comes from its vast bodies of liquid methane and ethane. These alien seas, the only known stable liquid bodies on the surface of another world, present an unfamiliar environment. On Earth, water is the liquid of life, essential for survival, but on Titan, liquid hydrocarbons dominate, filling massive lakes that stretch for hundreds of miles. The largest of these, Kraken Mare, is bigger than the Great Lakes combined. Falling into one of Titan's methane lakes would be a disaster. Unlike water, which is dense and provides buoyancy, methane and ethane are far less supportive. A person who fell into one of these alien lakes would sink more quickly than in water, slipping beneath the surface into an abyss of cold, oily darkness. The liquid, denser than air, but far less dense than water, would feel unfamiliar against the skin. Thinner, slipperier, almost frictionless. Struggling would do little good. The hydrocarbons provide little resistance, making it harder to stay afloat. There would be no natural reflex to cough or gag, no way to instinctively reject the liquid. If even a small amount of methane or ethane were inhaled, it would coat the lungs, blocking the exchange of oxygen. Unlike drowning in water, where the body fights against the sensation, the hydrocarbons would create an almost numb suffocation. Within moments, the cold would take hold, freezing exposed skin, numbing extremities, and robbing muscles of their ability to move. Even if a person could resurface, their body would be too stiff to function, their breath stolen by a liquid that was never meant to sustain life. Their body temperature would drop instantly, the heat drawn away by the extreme cold. Unlike water, which has a high heat capacity and takes time to pull warmth from a body, methane works faster, absorbing heat rapidly and making hypothermia almost immediate. Muscles would lock up, breath would become shallow, and within moments, all movement would cease. Any vehicle or craft attempting to operate on the surface of a methane lake would face unique challenges. Boats, if they could even function in such conditions, would have to be specially designed to handle the ultra-cold hydrocarbons. Traditional propulsion systems that work on Earth would fail in the thick, sluggish methane. And aircraft attempting to hover over the lakes would have to contend with Titan's thick atmosphere and unpredictable winds. Titan's lakes have waves, ripples, and tides driven by the gravitational pull of Saturn. These waves move more slowly, their motion dampened by the thick atmosphere and the unique properties of methane and ethane. A storm on Titan would not whip the seas into violent chaos the way a hurricane does on Earth. Instead, the movement would be slow and eerie, rolling in long, sluggish waves that move in near silence. Even the shoreline of Titan's lakes is treacherous. Unlike Earth, where beaches are made of sand and rock, Titan's shores are composed of organic compounds, frozen hydrocarbons that crunch underfoot like snow but lack the stability of solid ground. A person walking too close to the edge might find themselves slipping into the frigid liquid without warning. Triton's retrograde isolation, the icy death on Neptune's moon. Triton is unlike any other large moon in the solar system. It orbits Neptune in the wrong direction, moving in a retrograde path that suggests it was not born there, but was captured long ago. This backward motion shapes the entire fate of the moon. Triton is slowly spiraling inward, locked in a slow-motion death spiral that will one day see it torn apart by Neptune's gravity. The surface of Triton is the coldest known in the solar system, with temperatures plunging to nearly -235 degrees Celsius or -391 degrees Fahrenheit. Because of its distance from the Sun, Triton receives very little sunlight. It is also unusually reflective, with a high surface albedo. These two factors combined shape the conditions to be as absurdly cold as they are. At this temperature, nitrogen, normally a gas, freezes into solid sheets that coat the ground. The air is almost non-existent, a whisper-thin layer of nitrogen and trace gases that is so faint it barely qualifies as an atmosphere. There is no protection from the deep cold, no chance for warmth to linger. Anything exposed to the elements here would freeze instantly, its molecules slowing until they are locked in place by the sheer lack of heat. The ground is not simply frozen rock, but an ever-changing layer of exotic ices, frozen nitrogen, methane, and carbon monoxide, covering a crust that may be hiding a subsurface ocean deep below. Some regions are smooth, while others are marked by ridges and depressions shaped by unseen forces beneath the surface. The ice expands and contracts, cracking apart in places where internal heating causes the ground to shift. Jagged formations of nitrogen ice rise like frozen waves, creating treacherous, brittle terrain where every step could send chunks breaking away. Unlike regular moons that settle into stable orbits, Triton is being dragged backward against the direction Neptune rotates. The friction and stress created by this unusual motion generate internal heat, but not the kind that makes a place livable. Instead, it fuels a bizarre kind of geological activity, one that leads to icy eruptions rather than molten lava. Triton is home to active cryovolcanoes, cold geysers that blast plumes of nitrogen gas and icy particles miles above the surface before they fall back down in a gentle, deadly snowfall. These eruptions happen because sunlight, though weak at Neptune's distance, seeps just deep enough to warm frozen nitrogen layers beneath the surface. The trapped gas builds pressure until it explodes outward, sending dark plumes into the sky. Anyone standing near such an event would have almost no warning before the surface beneath them cracked apart, launching them into a blizzard of nitrogen snow and frozen debris. The force of these eruptions is enough to eject material far beyond the surface, even into space. Triton's geysers release gas that almost immediately refreezes into tiny ice particles, creating misty clouds of frozen death. The thin atmosphere offers no protection from Neptune's harsh radiation, or from the vacuum of space. While Triton's surface gravity is weak, it is still strong enough to hold down a whisper-thin layer of nitrogen gas. But this is not an atmosphere that can support anything living. It is a transition zone between the ice below and the emptiness above. Any person unlucky enough to be stranded on Triton without a pressurized suit would face immediate suffocation. The lack of pressure would cause bodily fluids to boil away, creating an agonizing death long before the cold could finish the job. Triton's sky is a dim, eerie place. Neptune looms above, a massive blue giant wrapped in swirling clouds. But the light reaching Triton is weak. At 30 times the Earth-Sun distance, the Sun appears no brighter than an ordinary full moon does on Earth. Shadows are long and sharp, cast in a pale twilight that never quite fades. This faint illumination creates strange lighting effects, making the ice formations glisten in unnatural ways. The ground seems to glow in places, reflecting the dim sunlight off surfaces of frozen nitrogen. At some distant point in the future, Neptune's gravity will win. Triton will cross the Roche limit, the point where tidal forces from the planet become stronger than the Moon's own gravity. When that happens, Triton will be torn apart. It will shatter into fragments, forming a ring of debris around Neptune that may resemble Saturn's rings. Jupiter's crushing embrace. Jupiter is the largest planet in the solar system, a world so massive that more than 1,300 Earths could fit inside it. But there is no solid ground to stand on, no surface that offers refuge. It is a planet made almost entirely of gas, a swirling giant of hydrogen and helium, where pressure and gravity work together to create one of the most extreme environments imaginable. Falling into Jupiter is an irreversible plunge into crushing darkness, where storms rage for centuries and gravity tightens its grip with every passing second. The upper atmosphere of Jupiter seems familiar at first. From a distance, its bands of clouds stretch across the planet in soft, sweeping currents of white, red, and brown. These are not ordinary clouds. They are thick layers of ammonia, methane, and other complex chemicals that swirl in patterns shaped by Jupiter's powerful winds. Here, at the outermost boundary, the gravity is already much stronger than on Earth, about 2.5 times as powerful. Moving in this environment would feel heavier, as if invisible hands were pulling downward, making every motion sluggish and difficult. But this is only the beginning. Jupiter's atmosphere is layered, with each level becoming more hostile than the one above it. The winds at the top move at incredible speeds, reaching up to 400 miles per hour. These violent gusts carve through the clouds, shaping these ever-changing structures. Thunderstorms the size of entire continents rage beneath the surface, their lightning bolts striking with 100 times the power of Earth's strongest storms. Falling through this chaos would be like plunging into an endless hurricane, where the wind never stops and the sky is a battlefield of energy. Jupiter's magnetic field is the strongest of any planet in the solar system, extending millions of miles into space. This field traps radiation in powerful belts that encircle the planet, creating an environment more radioactive than anything on Earth. The doses of radiation near Jupiter's largest moons are hundreds of times greater than a lethal dose for a human. A spacecraft passing too close without protection would be fried by the relentless bombardment of energetic particles. Any human exposed to this radiation for even a short period would suffer severe damage at the cellular level, with organs failing long before the crushing pressure of the planet itself took over. The Great Red Spot, Jupiter's most famous storm, has been churning for hundreds of years. It is a massive vortex, more than twice the size of Earth, where winds circle in a perpetual spiral. Unlike hurricanes on Earth, which lose strength when they pass over land, Jupiter's storms never encounter anything solid to stop them. They rage on, fueled by the planet's internal heat and immense gravity. Getting caught in one would mean being tossed violently, spun around in hurricane-force winds, unable to escape as the storm pulls downward. As the descent continues, the pressure begins to mount. The deeper one falls into Jupiter, the more crushing the atmosphere becomes. At 10 times the Earth's atmospheric pressure, the human body would start to struggle. The lungs would collapse, unable to expand against the increasing weight of the air. Every breath would become harder until breathing was no longer possible. Blood vessels would begin to burst, eyes would swell, and the body would be squeezed by the sheer force of the environment. Deeper still, the air turns darker. The sunlight from above fades, swallowed by the thickening layers of gas. The ammonia clouds give way to deeper layers of water vapor and hydrogen. The temperature rises, but unlike on Venus, where the heat radiates outward, Jupiter's heat comes from within. The planet generates more energy than it receives from the sun, warming its interior in ways that create towering storms and powerful jet streams. At a depth where the pressure is 100 times greater than Earth's, the human body would no longer resemble its original form. The sheer force of the atmosphere would have already crushed bones, flattened organs, and removed all air from the body. Beyond this point, the air itself begins to change. Hydrogen, the most abundant element in Jupiter's atmosphere, is forced into a new state under extreme pressure. It turns into liquid, flowing in great waves through the planet's deeper layers. This is the beginning of the metallic hydrogen region, Here, hydrogen behaves like a metal, conducting electricity and fueling Jupiter's massive magnetic field. The crushing weight above continues to intensify, reaching levels that no human body could ever endure. By the time the descent reaches depths, where the pressure is millions of times greater than on Earth, the journey becomes theoretical. No probe has ever survived this deep, and no material known to humanity could withstand such forces. The crushing pressure would reduce anything to atomic fragments long before reaching the mysterious core. Scientists believe that deep within Jupiter, beneath the metallic hydrogen layer, lies a core of rock and ice. But this core, if it exists, is not like the solid ground of Earth or the rocky surfaces of other planets. It is likely surrounded by a slushy, high-pressure ocean of exotic materials, compressed into strange states that cannot be recreated in any laboratory. If a human or spacecraft somehow made it this far, survival would be impossible in every conceivable way. The weight of the atmosphere would be beyond comprehension, thousands of times stronger than the deepest parts of Earth's oceans. The heat would be intense, possibly tens of thousands of degrees, hotter than the surface of the Sun. Any object that reached this point would not remain intact. It would be crushed, dissolved, and absorbed into the planet itself, becoming part of Jupiter's massive, swirling interior. There is no final impact, no place to land, no solid ground waiting at the bottom of the atmosphere. The descent would never truly end. It would simply continue until the falling object was broken down completely, consumed by the overwhelming pressure and heat. The gravity that first pulled the object in would never release its hold, drawing everything deeper into the heart of the gas giant until there was nothing left to distinguish it from the planet itself. Saturn's ringed perils. Saturn is known for its rings, a breathtaking display of cosmic beauty stretching over 170,000 miles across. From a distance, they appear smooth and delicate, like a painter's brush strokes across the night sky. Up close, they are a chaotic landscape of ice and rock, where high-speed collisions are constant and survival is impossible. The rings are not solid structures, but countless particles ranging from tiny dust grains to house-sized boulders, all moving at incredible speeds. Navigating through them would mean facing a relentless bombardment of high-speed debris, each fragment a potential threat. The rings themselves are remarkably thin, sometimes only a few meters thick, yet they stretch so wide that they could fit several Earths across their diameter. They are made mostly of ice, but the occasional rock or carbon-rich fragment lurks within them, a silent projectile waiting to strike anything that dares to pass through. Each piece moves at tens of thousands of miles per hour, faster than a bullet. A spacecraft attempting to navigate through these rings would be battered from every angle, its surface scarred by relentless impacts. Even the smallest fragment, no bigger than a pebble, would hit with enough force to tear through metal and shatter equipment. A person caught in this environment would have no chance. Like Jupiter, it is a gas giant with no solid surface, only an endless descent into thickening clouds and crushing pressure. The planet's upper atmosphere appears calm in some regions, but the deeper one goes, the more chaotic it becomes. Winds whip around Saturn at over 1,000 miles per hour. These are not temporary storms, but permanent jet streams. A human falling into Saturn would be caught in a violent current, spun in every direction by winds so strong that they could tear apart anything in their path. The deeper layers of Saturn are shrouded in mystery. No spacecraft has ever survived long enough to send back information about what lies below the visible clouds. Scientists believe that, much like Jupiter, Saturn's hydrogen atmosphere gradually transitions into a thick ocean of metallic hydrogen. This ocean, if it exists, is likely thousands of miles below the clouds, hidden beneath crushing pressure and extreme temperatures. A human falling this deep would never reach it intact. The body would be obliterated long before. Unlike the chaotic swirling clouds of Jupiter, Saturn's storms form in strange geometric patterns, the most famous being the hexagonal storm at the planet's north pole. This massive vortex is nearly 20,000 miles wide, large enough to swallow multiple Earths. The winds within it are fierce, swirling in a six-sided shape that has remained stable for decades. What causes this unique storm to form in such a precise pattern is still a mystery, but what is certain is that any object caught in its grasp would be trapped in an endless whirlpool of wind and pressure. There would be no escape, only a relentless spiral downward into the unknown. Uranus's tilted abyss, icy winds and lateral dangers. While most planets rotate upright or with a slight tilt, Uranus lies on its side, tilted at an extreme 98 degrees. This bizarre orientation creates a unique environment. Instead of experiencing day and night cycles like Earth, Uranus has entire hemispheres plunged into darkness for decades at a time, only to switch to months of continuous daylight. This extreme shift in sunlight exposure leads to wild temperature fluctuations and chaotic atmospheric movements. The planet's pale blue color gives the impression of a calm, frozen world, but beneath its cloud tops, Uranus is a place of violent and unpredictable weather. Its atmosphere is mostly hydrogen and helium, but unlike Jupiter and Saturn, it also contains high concentrations of methane. This methane absorbs red light and scatters blue, creating its distinct icy appearance. But the real threat lies in the winds, some of the most erratic in the solar system. Unlike on Earth, where winds move mostly east or west due to the planet's rotation, Uranus's sideways tilt causes its winds to shift in unexpected directions. These winds don't just move around the planet's equator, they can swirl in strange lateral patterns, creating a chaotic and unpredictable atmosphere. Falling into Uranus's upper atmosphere might seem like entering a cold, thick fog at first, but this illusion would quickly fade. At first, the body would feel the weight of the atmosphere pushing inward, making every movement more difficult. Breathing would already be impossible, but the true danger comes from the winds. Unlike on other gas giants, where storms swirl in mostly vertical columns, Uranus's winds can hit from unexpected angles. One moment, a falling body might be caught in an upward draft, flung violently back toward the upper layers. The next moment, a powerful lateral gust could slam it sideways at hundreds of miles per hour, twisting and contorting it before pulling it deeper into the abyss. These winds alone would be enough to make survival impossible, but the extreme cold adds another layer of danger. Uranus is the coldest planet in the solar system, reaching temperatures as low as -223 degrees Celsius or -371 degrees Fahrenheit. This is even colder than Neptune, which is farther from the Sun. Scientists believe Uranus's frigid nature is due to a lack of internal heat. Unlike Jupiter and Saturn, which radiate heat from their interiors, Uranus barely emits any warmth at all. This means that once an object is caught in its icy clouds, there is no escaping the relentless cold. Any exposed skin would freeze almost instantly. The moisture in the eyes, mouth and lungs would turn to ice, crystallizing before there is even time to react. The body would become stiff, its functions shutting down as the frozen environment saps away all remaining heat. Uranus, like Neptune, is classified as an ice giant, meaning that beyond its swirling clouds lies a deep ocean of icy, slushy materials. Water, ammonia, and methane in a strange high-pressure state. Scientists believe that this ocean doesn't behave like Earth's liquid water, but instead forms a dense, churning layer that becomes more pressurized with depth. The pressure would squeeze the body tighter and tighter, bones snapping, organs collapsing, until there was nothing left but a compacted mass of frozen remains. Uranus is still full of mysteries. Its unusual tilt suggests a violent past. Scientists believe that at some point in its early history, a massive impact from a planet-sized object knocked it onto its side. This collision likely reshaped the planet's interior. The impact may have also influenced its strange magnetic field, which is tilted at an angle and doesn't align with the planet's rotation. Unlike Earth's magnetic field, which is relatively stable, Uranus's magnetic field wobbles unpredictably. Because of its sideways rotation, each pole spends about 42 years in constant daylight, followed by 42 years of complete darkness. During these long seasons, the winds shift in strange ways, sometimes slowing to a near stop, only to accelerate unpredictably. The transition between these seasons can be violent, triggering massive storms that stretch for thousands of miles. Neptune's ferocious storms, expiring in a deep blue tempest. Neptune is a world of chaos, where winds scream across its blue surface at speeds unmatched by any other planet in the solar system. The planet's winds reach up to 1,200 miles per hour, faster than the speed of sound on Earth. These winds don't just push the air around, they create massive storms, some of which are larger than Earth itself. The most famous of these storms was the Great Dark Spot, first observed in 1989 by the Voyager 2 spacecraft. It was similar in appearance to Jupiter's Great Red Spot, but instead of a swirling, stable hurricane-like system, Neptune's storm was a violent, fast-moving vortex that shifted unpredictably. By the time telescopes looked for it again a few years later, it was gone, replaced by new storms forming in different regions of the planet. This unpredictability is one of Neptune's most dangerous traits. Storms can appear anywhere, at any time, with no warning. A body falling into these winds would be tossed and battered. The force of these winds would be enough to strip away any protective layers, tearing apart anything not built to withstand extreme pressure. The air would become a lethal weapon, slamming into the body with such force that bones would shatter, and internal organs would rupture from the impact. Deeper still, the temperature begins to rise. Unlike Uranus, which barely emits any internal heat, Neptune radiates a surprising amount of warmth from within. Scientists aren't sure why, but this heat source creates a dynamic atmosphere where storms can feed off rising energy, becoming stronger and more violent the further down one goes. The winds, instead of weakening, intensify. Cloud layers form at different altitudes, each bringing its own dangers. The highest clouds are made of methane ice, floating like frozen wisps in the upper atmosphere. But deeper down, clouds of ammonia and hydrogen sulfide create thick, choking layers that swirl unpredictably. The deeper layers may contain superheated water trapped under immense pressure, behaving more like a dense fluid than a typical gas. Even if somehow a structure could withstand the pressure, there would be no stopping the descent. Neptune transitions from gas to an increasingly dense fluid, eventually leading to a strange ocean-like interior. This ocean is a superheated high-pressure mixture of hydrogen, helium and other elements, forming a dense slushy layer that extends for thousands of miles. At the deepest levels, temperatures soar to thousands of degrees, and the crushing pressure is millions of times greater than on Earth's surface. It is here that an object would be fully consumed, compacted beyond recognition before dissolving into the churning depths of the planet. Pluto's lonely icy tomb. Final moments in the Kuiper Belt. Pluto drifts in the frozen outskirts of the solar system, where the sun is nothing more than a distant point of light. Unlike the inner planets, where storms rage and heat scours the surface, Pluto's dangers come not from violent forces, but from the slow, creeping grasp of isolation and cold. It is a place where temperatures plunge so low that the air itself can freeze and fall as snow. Standing on Pluto's surface, there would be no sound. The thin atmosphere, composed mostly of nitrogen with traces of methane and carbon monoxide, is barely enough to carry the faintest whisper of a breeze. The pressure is a fraction of what is found on Earth, far too thin to breathe. It is not a place where life could hold on. The cold here is absolute. The surface temperature hovers around -235 degrees Celsius, similar to Triton, and is cold enough to turn even familiar gases into solid ice. At these temperatures, oxygen, nitrogen, and carbon dioxide would freeze instantly, forming brittle crystals in the air. The simple act of breathing would be impossible. not only due to the lack of oxygen, but because even attempting to inhale would cause lung tissue to freeze from within. With an atmosphere nearly 100,000 times thinner than Earth's, the body would be exposed to near vacuum conditions. Without a protective suit, the moisture in the lungs and eyes would boil away. This would not be a burning sensation, but rather a rapid loss of fluids as they turn to vapor. Blood vessels in the skin would rupture, causing swelling as gases expand within the body. Unlike in deep space, where unconsciousness comes within seconds, the presence of even a slight atmosphere on Pluto might delay complete incapacitation, stretching the suffering into minutes rather than seconds. Even with a protective suit, the cold would seep into every material, freezing equipment and stiffening joints. Metals would be vulnerable to snapping like fragile glass. Electronics would struggle to function, batteries would drain rapidly, and any exposed material would become so cold that touching it would cause instant frostbite. Any warmth a person could generate would be lost almost immediately, radiating away into the vast emptiness of space. The landscape itself is a frozen wasteland, covered in nitrogen ice and dotted with jagged mountains of frozen water. Unlike Earth's mountains, which are shaped by erosion, wind and rain, Pluto's are sculpted by the slow movement of glaciers and the gentle settling of ice layers over millions of years. Shadows cast by these towering formations stretch for miles under the dim sunlight, never changing, never shifting. Time moves differently here, not in days and nights, but in vast geological ages, where a single season can last for more than a century. Pluto's orbit takes it on a long, elliptical journey around the Sun, swinging it far beyond Neptune before bringing it slightly closer again. At its most distant, the sunlight is so weak that it barely illuminates the surface, casting an eerie glow over the frozen plains. At its closest, Pluto's tenuous atmosphere expands as some of its surface ice sublimates into gas, forming a thin temporary shroud around the dwarf planet. But as it drifts outward again, the cold reclaims its hold, and that fragile atmosphere collapses back onto the surface, turning into frost that settles over the land. The remoteness of Pluto is another silent danger. Unlike Mars, which at least holds the potential for human exploration, Pluto is so far removed from Earth that any rescue mission would be impossible. A signal sent from Pluto takes more than 4 hours to reach Earth, meaning that even in the best-case scenario, there would be no immediate help, no quick response. Any traveler who found themselves stranded on this distant world would be entirely alone, with no hope of rescue. It would be the ultimate isolation, trapped on a frozen rock at the edge of the solar system, with nothing but the silent expanse of space, stretching infinitely in all directions. Black holes and spaghettification, a cosmic death sentence. Formed from the collapse of massive stars, black holes warp space and time in ways that defy common sense. Their boundaries, called event horizons, mark the point of no return. Anything that crosses this invisible threshold is lost forever. For anything unfortunate enough to come too close, the journey into a black hole is a slow, inevitable fall into destruction. The most horrifying fate inside a black hole is spaghettification. This is the process where intense gravitational forces stretch and pull apart objects until they become long, thin strands, like spaghetti. The reason this happens is that gravity acts with different strengths on different parts of an object. If a person were falling feet first toward a black hole, the gravity at their feet would be much stronger than at their head. The difference in force would grow extreme, stretching the body longer and longer, pulling bones, muscles, and tissues apart. At the same time, the sides of the body would be squeezed inward. This relentless stretching and squeezing would continue until the body was nothing more than a thin stream of atoms, spiraling down into the darkness. The process does not happen instantly. If the black hole is small, spaghettification begins outside the event horizon. The gravitational forces are so concentrated that an object would be torn apart even before crossing the threshold. For a large black hole, like the supermassive ones found in the centers of galaxies, the event horizon is farther away from the strongest gravitational forces. This means a person could actually pass the event horizon without noticing anything unusual at first. They would still be doomed, but they might not realize it immediately. Once past the event horizon, escape is impossible. Space itself is falling inward, dragging everything with it. Even light, which travels faster than anything else in the universe, cannot move fast enough to break free. From an outside observer's perspective, someone falling into a black hole would appear to slow down as they got closer to the event horizon. Their movements would stretch out, and they would seem to freeze in place, fading away as the light coming from them became redder and dimmer. But for the person falling, time would seem normal, even as they moved toward their inevitable fate. As the fall continues, gravity increases to unimaginable levels. Atoms themselves begin to break apart. Even the fundamental particles making up matter could be torn from each other, stretched into the very fabric of space. No information, no signal, no final cry for help can ever leave. The person, or whatever remains of them, is lost forever in the depths of the black hole. At the very center lies the singularity. This is a point where gravity becomes infinite and space and time collapse completely. Physics as we know it no longer makes sense in this region. What happens here is unknown. Some theories suggest that all matter and energy falling into the black hole is crushed into an infinitely small point. Others speculate that black holes might lead to other parts of the universe or even different universes altogether. But there is no way to know for sure because nothing can escape to tell the tale. Some black holes consume matter so rapidly that they unleash massive jets of energy, shooting out at nearly the speed of light. These energetic beams can stretch for thousands of light years, lighting up the universe like cosmic lighthouses. The feeding process is chaotic and deadly, with matter swirling around the black hole in a superheated disk before falling in. Temperatures in this disk can reach millions of degrees, producing intense radiation that could sterilize entire regions of space. There are also wandering black holes, rogue objects that drift through the galaxy, unseen and undetectable until it is too late. If one were to pass through our solar system, its gravity could disrupt planetary orbits, sending worlds crashing into each other or flinging them into deep space. Even without direct contact, its influence could cause catastrophic changes. The worst-case scenario would be an approach close enough to pull Earth toward its event horizon, dooming the planet to total destruction. There is no escaping the grasp of a black hole. No material, no technology, no force in the universe is strong enough to resist its pull once the event horizon is crossed. The final moments for anything falling in are unlike any other death in space, stretched beyond recognition, disintegrated down to the smallest components of existence, and erased from the universe with no possibility of return. Magnetar's magnetic overload, the human body under cosmic stress. A magnetar is a type of neutron star, born from the collapsed core of a massive star. But unlike ordinary neutron stars, magnetars possess magnetic fields trillions of times stronger than Earth's. These fields are strong enough to distort atoms, tear apart molecules, and wreak havoc on anything that comes too close. If a person were to approach a magnetar, they would not need to set foot on its surface to experience its lethal effects. The sheer strength of its magnetic field would reach out long before physical contact, pulling apart the very structure of their body at the atomic level. The human body relies on complex chemical and electrical processes to function. The brain communicates through electrical signals. The heart beats due to a delicate balance of ions, and every cell operates under finely tuned biochemical reactions. A magnetar's field would disrupt all of this instantly. As a person drew closer, the field would begin to interfere with neural activity, scrambling thoughts and distorting perception. The iron in the blood would be pulled in unnatural ways, potentially causing clots or internal bleeding. Even at great distances, the field is strong enough to erase data from electronic devices and disrupt fundamental biological processes. But at closer ranges, the effects become even more devastating. The atoms that make up human tissue would begin to stretch, their normal shapes distorted by the relentless pull of the magnetic field. Molecular bonds would weaken and snap, breaking down the structure of proteins, DNA, and cell membranes. The body would start to disintegrate at an atomic level, pulled apart by forces stronger than anything found on Earth. This would not be a slow process. The moment a person entered a sufficiently strong magnetic field, the destruction would be almost instantaneous. These stars are known to unleash violent eruptions called starquakes, caused when the intense magnetic stress builds up within their crust and suddenly shifts. These quakes release immense amounts of energy, producing gamma-ray and X-ray bursts strong enough to be detected across vast distances of space. A single burst from a magnetar could disrupt satellites and damage planetary atmospheres, even from thousands of light-years away. The energy from these outbursts is so extreme that if a magnetar were positioned within our solar system, even at a safe distance beyond Pluto, it could still be deadly. A single gamma-ray burst from a magnetar could strip away Earth's ozone layer, exposing the planet to lethal levels of ultraviolet radiation from the Sun. The radiation itself would be powerful enough to ionize the upper atmosphere, leading to massive electrical disturbances and widespread destruction of electronic systems. There is no way to shield against such forces. Traditional spacecraft, designed to withstand cosmic radiation and solar storms, would be utterly ineffective in the presence of a magnetar's field. Metals would become magnetized, circuits would fail, and no technology known to humanity could function within such an environment. Even approaching from a great distance would be risky. The immense gravitational pull of a magnetar, though not as extreme as a black hole's, is still formidable. If a spacecraft were to get too close, it could be drawn in, accelerating to extreme speeds before being torn apart by tidal forces. Magnetars are among the rarest objects in the universe, with only a handful known to exist. Yet their power extends far beyond their limited numbers. Their fields are so intense that they influence their surroundings even across vast distances. They are cosmic reminders of the extremes of physics. There is no surviving a magnetar's grasp, no resisting its pull. Super-Earths, the weight of alien gravity on life. Super-Earths are a class of exoplanets larger than Earth but smaller than Neptune. They range from just slightly bigger than our planet to nearly 10 times its mass. Some may have Earth-like conditions, but many are extreme environments where gravity itself would be the greatest hazard. On Earth, gravity shapes every aspect of life. Our bones, muscles, and circulatory systems evolved to function under a precise gravitational force. Walking, running, and even standing upright are second nature because our bodies are built to handle Earth's specific pull. But on a super-Earth, where gravity is much stronger, every movement would become an exhausting struggle. Even a planet with twice Earth's gravity would turn simple actions into strenuous tasks. The force keeping you pressed to the ground would be relentless. Lifting an arm, bending a knee, or even turning your head would feel like doing everything with heavy weights strapped to your body. Walking across a room could leave you gasping for breath as your muscles and heart work overtime. Running might be impossible. Jumping would barely lift you off the ground. Falling would be more dangerous as the increased acceleration would make even minor stumbles more forceful. A simple trip could result in broken bones, and an impact that might cause a bruise on Earth could rupture tissue or cause internal bleeding on a high-gravity world. For astronauts, adapting to such an environment would be nearly impossible without mechanical assistance. Even the strongest humans on Earth would struggle to stay on their feet. Special exoskeletons could help distribute weight and support movement, but the human body itself is not designed for such conditions. Long-term exposure would take a devastating toll. One of the biggest challenges would be the cardiovascular system. On Earth, the heart pumps blood upward against gravity, ensuring that oxygen reaches the brain. On a super-Earth, the force pulling everything downward would be much stronger. Blood would pool in the lower body, making it difficult for the heart to maintain circulation. Standing up too quickly could cause dizziness or unconsciousness as blood struggles to reach the brain. Over time, the the strain on the heart could lead to failure. Even bones, which are constantly regenerating to maintain their strength, would suffer. In response to higher gravity, bones would thicken over generations, but this wouldn't happen fast enough for someone arriving from Earth. The additional stress could lead to fractures and joint degeneration. Muscles, too, would have to work much harder. Without extensive training, most people wouldn't be able to function. The elderly, children, or those with existing health conditions would be at an even greater risk. Mountains, limited by the force of gravity, would be shorter and more compressed. The tallest peaks on Earth are possible because rock can support itself under our specific conditions. But on a super-Earth, gravity would limit how high solid land can rise before collapsing. Similarly, trees and plants might grow shorter and sturdier, as tall, slender structures would be more likely to buckle under their own weight. Oceans, too, would be affected. The pressure at depth would be far greater than anything on Earth, making deep-sea exploration even more dangerous. Water molecules themselves would be squeezed more tightly, possibly changing the way ocean currents and weather patterns behave. If the planet had a dense atmosphere, storms could be more intense, with heavier rain and stronger winds. The weight of the air itself could make breathing difficult, especially if the atmosphere was thick and compressed. For any life that evolved on a super-Earth, adaptation would be key. Native animals would likely be stockier and more muscular, with strong limbs to support their weight. Flight might be nearly impossible unless the atmosphere was thick enough to provide additional lift. Even then, wings would need to be massive and incredibly powerful. Any intelligent beings living on such a planet would likely have different body structures than humans, built to endure constant gravitational stress. If a civilization arose on a high-gravity world, space travel would be another major obstacle. On Earth, rockets need to reach speeds of about 40,000 kilometers per hour to break free from our planet's gravity. On a super-Earth, escape velocity would be much higher. Launching a spacecraft would require much more fuel and stronger engines. A civilization at the same technological level as present-day Earth might struggle to develop space travel at all. Even if they had advanced technology, the sheer energy cost of leaving their planet could make interstellar exploration far less common. If humans ever attempted to colonize a super-Earth, they would need to rely on extensive genetic modifications or artificial enhancements. Over generations, human settlers might evolve thicker bones, stronger muscles, and more efficient circulatory systems, but such changes would take time. Until then, survival would depend on technology, exoskeletons, pressure suits, and artificial gravity environments to reduce stress on the body. Hot Jupiters, incineration by extreme stellar proximity. Hot Jupiters are gas giants that orbit their stars at incredibly close distances, with some completing a full revolution around their stars in just a few days. Their proximity exposes them to intense stellar radiation, scorching heat, and powerful gravitational forces. Unlike the cold, distant gas giants of our solar system, these planets live on the edge of survival, their atmospheres boiling away under the relentless energy of their parent stars. The heat on a hot Jupiter is almost unimaginable. Many of these planets experience temperatures exceeding 2,000 degrees Celsius, hot enough to melt iron. Some of the hottest, like Kelt 9b, have atmospheres reaching over 4,000 degrees Celsius, making them hotter than some stars. At these temperatures, normal matter behaves differently. Metals can turn into vapor, and molecules struggle to remain intact. The upper layers of these planets' atmospheres are constantly bombarded by intense radiation, stripping away lighter elements and causing the planet to lose mass over time. A human exposed to such an environment would be vaporized instantly. The heat would tear apart organic molecules before the body even had a chance to ignite. Spacesuits or any known material would offer no protection, as even the most heat-resistant substances would break down under such extreme conditions. The sheer energy pouring from the nearby star ensures that survival is not just impossible, it is unthinkable. The atmosphere of a hot Jupiter is in constant turmoil. Winds can reach speeds of thousands of kilometers per hour, driven by the extreme temperature differences between the star-facing side and the cooler, shadowed hemisphere. These winds redistribute heat across the planet, but they also create violent storms of a scale unknown anywhere in our solar system. Some hot Jupiters may experience continuous planet-wide cyclones that never dissipate, their skies filled with turbulent, roiling clouds of exotic chemicals. Many of these planets are tidally locked, meaning one side always faces the star, while the other remains in eternal darkness. The day side experiences unending radiation, while the night side endures a sharp temperature drop. This imbalance can create violent atmospheric currents as heat surges from one hemisphere to another. The extreme temperature differences could also lead to strange and deadly forms of precipitation. Scientists believe that on some hot Jupiters, molten glass or even liquid iron may rain from the sky, propelled sideways by the howling winds. Because hot Jupiters orbit so close to their stars, they are bathed in intense ultraviolet and X-ray radiation. This energy blasts their atmospheres, stripping away hydrogen and helium and gradually eroding the planet over time. Some hot Jupiters are slowly evaporating, their gases trailing behind them like a comet's tail as they lose material to space. Any spacecraft or human visitor attempting to explore such a world would be bombarded by lethal doses of radiation long before reaching the surface. Many hot Jupiters experience tidal forces so strong that they become stretched into slightly elongated shapes rather than perfect spheres. Their close orbits can also create extreme gravitational interactions with their parent stars, affecting their rotation and orbital stability. In some cases, the gravitational pull of the star may eventually cause the planet to spiral inward, dooming it to be consumed in a final fiery collision. Some of these planets have atmospheres rich in exotic compounds, including titanium oxide, vanadium, and carbon monoxide. These elements, rarely found in large quantities on cooler planets, dominate the high-temperature chemistry of hot Jupiters. The result is an alien world where clouds of vaporized metals swirl through superheated air and toxic gases fill the skies. Breathing in such an atmosphere, if that were even possible, would mean immediate poisoning and suffocation. Some hot Jupiters display even stranger phenomena. There are planets where one side glows a deep red from the constant heat, while the other side remains in darkness. Others reflect almost no light, appearing as pitch-black orbs against the backdrop of space. Some have clouds made of rock, where silicate particles form high in the atmosphere before falling as molten rain. Each discovery reveals new ways these planets challenge the limits of survival. The fate of a hot Jupiter is often sealed from the moment it forms. Over time, many will lose their atmospheres entirely, leaving behind only a scorched, rocky core. Others may be pulled into their stars, vanishing in a final burst of energy. Some may even be ejected from their orbits, cast into the depths of space as rogue planets, forever drifting in the cold darkness after spending their existence in unbearable heat. Rogue planets, isolation, and the desolation of the cosmic void. Rogue planets drift through the cosmos, untethered to any star, wandering endlessly in the cold, dark expanse of interstellar space. Unlike planets bound to a solar system, these worlds are alone, moving through the void without the warmth of a sun to sustain them. They may have once belonged to a planetary system, only to be flung away by gravitational forces, or they may have formed in isolation, never knowing the steady pull of a central star. The most immediate and overwhelming danger of a rogue planet is the complete absence of sunlight. In a typical solar system, a star provides heat, energy, and the conditions necessary for liquid water and atmospheric stability. Without a star, a rogue planet is shrouded in darkness. There is no natural day-night cycle, no seasons, and no external heat source to maintain warmth. Over time, Any surface water would freeze into a solid crust, and the planet's atmosphere, if it had one, would condense and collapse as temperatures plummeted. A planet like Earth, if ejected from its solar system, would see its surface temperature drop rapidly. Within weeks, the oceans would begin freezing over. The atmosphere, now devoid of any heat input, would become dangerously cold. Carbon dioxide in the air would freeze and fall as snow, and nitrogen would eventually condense as well. The surface would become a frozen wasteland, with any remaining heat trapped deep below the crust. For any life that remained, survival would depend entirely on the planet's internal heat. Some rogue planets may still have active geothermal energy from radioactive decay or residual heat from their formation. If so, the only habitable environments would exist deep underground, where warmth from the planet's core could sustain subsurface lakes or hydrothermal vents. Just as life exists in Earth's deep oceans near volcanic vents, similar extremophiles could theoretically survive on a rogue planet, but only in isolated pockets. For a human attempting to survive on such a world, the obstacles would be nearly insurmountable. With no sunlight, solar power would be useless. There would be no natural light, leaving everything in perpetual darkness. Even if the planet had some geothermal energy, it would not be enough to sustain large-scale human settlements. The lack of heat, food sources, and breathable air would make long-term survival almost impossible. In the total darkness of a rogue planet, navigation would require artificial lighting at all times. The frozen landscape would be treacherous, with unpredictable terrain shaped by ice flows, collapsing crust, and possibly hidden geysers where geothermal heat still seeps through. Temperatures could drop to hundreds of degrees below freezing, making exposure deadly within minutes. If the planet still had an atmosphere, it would likely be thin and unstable. Without a star's radiation to sustain atmospheric processes, gases would gradually freeze or dissipate. Winds and weather, once driven by temperature differences between day and night, would slow or stop entirely. If an atmosphere did persist, it could be toxic or unbreathable, with high concentrations of frozen carbon dioxide and nitrogen. Breathing without a pressurized suit would be impossible. One of the most terrifying aspects of a rogue planet is the sheer isolation. In a solar system, planets are part of a dynamic environment, orbiting a central star with the possibility of communication, exploration, and resource sharing. A rogue planet, by contrast, is completely alone. There are no nearby worlds to visit, no external sources of energy, and no way to call for help. Even if a human colony somehow managed to establish itself, it would exist in total solitude, cut off from the rest of the universe. If a rogue planet had a thick enough atmosphere or active volcanic activity, it might retain some heat beneath its surface. In rare cases, it could even have subsurface oceans protected by a layer of ice. Some scientists speculate that under the right conditions, such planets might even harbor life, living in isolated ecosystems fueled by chemical reactions rather than sunlight. These hypothetical organisms would rely on chemosynthesis, much like bacteria found near hydrothermal vents on Earth's ocean floor. Water worlds, suffocation under endless alien oceans. Water worlds, planets covered entirely by vast, unbroken oceans, offer an environment where the very element that sustains life can also bring about a slow and suffocating demise. These planets, with no land to stand on and no surface features beyond an endless expanse of liquid, would be an alien and hostile environment for humans to encounter. With no solid ground, there is nowhere to rest, build shelter, or establish a foothold. Even with advanced technology, maintaining a stable existence would require either floating structures or fully submerged habitats. Unlike Earth's oceans, which cover only part of the surface and have continents rising above them, a true water world has no such variation, only a single global sea that stretches beyond the horizon in every direction. Even if survival above the water was somehow managed, another significant threat would come from what lies below. Unlike the oceans of Earth, where the deepest points reach only about 11 kilometers, The oceans of a water world could be hundreds or even thousands of kilometers deep. Without tectonic plates or a rocky surface near the top, these depths would be filled entirely with water, creating immense pressures that would crush anything that sank too far. A human diving into these waters without proper protection would quickly reach a depth where the weight of the water above becomes unbearable. Even specialized submarines designed for extreme depths on Earth might struggle against the crushing forces of an ocean that extends far beyond what our planet's seas ever reach. The deeper one goes, the darker and colder the environment becomes. Sunlight can only penetrate the upper layers, leaving the depths in perpetual darkness. Any hope of exploration beneath the surface would require artificial lighting and pressurized vehicles capable of withstanding enormous forces. The deeper waters of a water world could contain unusual forms of life, adapted to conditions completely unlike anything found on Earth. Strange bioluminescent creatures, towering underwater ridges, and vast currents shaped by planetary forces might exist in these unseen depths. While a water world may have a thick, water vapor-rich atmosphere above its ocean, it may lack the oxygen necessary for breathing. Even if the air contained some form of breathable gas, the immense humidity and constant exposure to evaporating water could make respiration difficult. The air could be so thick with moisture that breathing would feel like inhaling steam, leading to suffocation even above the water's surface. Without land to break up wind patterns, hurricanes, cyclones, and other storms could rage unchecked, growing to immense sizes. Winds could reach speeds far beyond what is seen on Earth, and waves could stretch for kilometers, crashing endlessly across the ocean's surface. Anyone caught in such a storm would have no shelter to retreat to, and no way to escape the relentless forces of wind and water. Even advanced floating structures could struggle to remain intact in the face of such extreme weather, making long-term survival incredibly difficult. Earth's oceans remain largely unexplored, and even here we find bizarre creatures that thrive in conditions once thought impossible for life. On a water world where the ocean extends for hundreds or thousands of kilometers, the unknown is even more terrifying. There could be enormous creatures adapted to high-pressure environments, moving through the deep in total darkness. Some of these beings might be harmless, drifting through the abyss in search of microscopic food sources. Others could be predators unlike anything seen before, ruling the vast and empty spaces below the surface. For a human visiting a water world, the best hope for survival would be in artificial structures capable of withstanding both the surface storms and the crushing depths. Floating colonies, designed to endure massive waves and extreme weather, might allow some measure of stability. Submerged bases, resting just below the surface, could protect against the worst of the planet's atmosphere, while still allowing access to vital resources. But the dangers would always be present. One storm, one equipment failure, or one unexpected event could quickly turn survival into an impossibility. Despite these dangers, water worlds remain some of the most intriguing possibilities in the search for extraterrestrial life. If life exists beyond Earth, it may very well be in the oceans of these distant planets, thriving in conditions that would be fatal to humans, but perfectly suited to alien organisms. Lava worlds, the cataclysm of volcanic exoplanets. Somewhere beyond our solar system, there are planets where the surface is an unbroken sea of molten rock, glowing with the heat of constant eruptions. These are lava worlds, exoplanets so close to their stars or so geologically active that their landscapes never cool. There is little stable ground to stand on, just a shifting, restless expanse of liquid fire. Every moment on such a planet is marked by violent eruptions, the air choked with volcanic gases, and the temperature soaring to levels that would vaporize anything unprotected. Some of these planets are locked in tight orbits around their stars, constantly bombarded by radiation and heat that pushes their surface temperatures into the thousands of degrees. Even metals with high melting points would become soft and unworkable in such an environment, and protective suits would be useless. The moment any unprotected object entered the atmosphere of a lava world, it would start to disintegrate. The air itself would be just as deadly as the molten terrain below. A planet dominated by volcanic activity would have an atmosphere thick with carbon dioxide, sulfur dioxide, and other toxic gases. Breathing would be impossible, even with advanced life support, because the sheer concentration of these gases would corrode equipment and eat away at any protective barriers. The pressure in some cases might be immense, with thick clouds trapping heat and forming a runaway greenhouse effect that keeps the planet permanently searing. Unlike on Earth, where volcanic gases eventually dissipate, a lava world would constantly replenish its poisonous atmosphere, making survival impossible for any life as we know it. The surface never truly solidifies. Instead, massive rivers of molten rock flow in every direction, creating new landscapes only to erase them moments later. Explosive eruptions send towering plumes of molten rock and ash into the sky, covering everything in fire and debris. Some of these eruptions could be strong enough to send lava fountains miles high, raining down molten rock across the entire planet. Anyone unfortunate enough to be caught in such an environment wouldn't even have time to react before being consumed by fire or suffocated by the thick volcanic ash. One of the most extreme lava worlds discovered is K2-141b, an exoplanet so close to its star that its day side is a permanent inferno. On this planet, rock doesn't just melt, it vaporizes, forming a bizarre cycle where stone itself becomes part of the atmosphere. The intense heat causes sodium, silicon, and iron to evaporate and rise into the air like water vapor on Earth. High-altitude winds then carry these vaporized minerals to the planet's colder, dark side, where they cool and condense, falling back down as molten rock rain. This creates a never-ending loop, a planet where it literally rains lava, recycling its own surface through an alien version of Earth's water cycle. The winds on some lava worlds may be fast enough to shred apart anything that enters their atmosphere. Because of the extreme temperature differences between the molten side and the cooler regions, powerful atmospheric currents sweep across the surface at thousands of miles per hour. Any attempt to land on such a world would be met with hurricane-force winds carrying ash, molten droplets, and searing gas. Unlike Earth's storms, which bring rain and wind, these tempests would carry particles of vaporized rock, scouring and melting anything exposed to them. Any structure hovering over a lava world would be subject to constant heat exposure, causing materials to expand, weaken, and eventually fail. Any attempt to extract samples or study the surface up close would be nearly impossible, as even the most heat-resistant materials known to science would struggle to endure the intense environment. Some lava worlds may have cores that churn with even greater intensity than their molten exteriors, generating powerful magnetic fields and unpredictable geological activity. Earth experiences quakes due to shifting tectonic plates, but on a lava world, the entire crust may be in constant motion, creating rolling waves of molten rock that never stop. Gigantic lava lakes might form and collapse without warning, and towering plumes of superheated gas could burst from below, turning any stable area into an immediate death trap. If someone found themselves in an orbiting station above such a planet, the environment would still pose relentless challenges. Radiation from the nearby star would be intense, and the planet's own extreme temperatures could disrupt equipment and make prolonged observation risky. Lava worlds are a testament to the raw power of planetary formation. In some cases, they are young planets, still in the process of cooling from their violent births. Others have been trapped too close to their stars, permanently stripped of any chance to form solid ground. Some might even be remnants of former gas giants, their atmospheres burned away until only a molten core remains. For any human, these worlds are the epitome of inhospitable environments. They are places of unrelenting destruction, where fire and rock dominate in a never-ending cycle of renewal and annihilation. Carbon planets demise in a diamond-rich, exotic terrain. Out there in the universe, there may exist carbon planets, worlds where carbon rather than oxygen or silicon dominates the landscape. They are strange alien places where graphite mountains rise under a sky filled with soot, and vast plains of hardened hydrocarbons stretch to the horizon. Beneath the surface, pressure and heat may have turned much of the planet's interior into pure diamond, creating a core more valuable than anything humanity has ever seen. But beauty does not mean safety. These exotic worlds are not welcoming. Instead of familiar rocky terrain, the ground could be covered in layers of tar-like hydrocarbons, forming vast sticky fields that stretch for miles. Moving across such terrain would be nearly impossible, as the thick deposits could trap anything that ventured into them. A person could sink slowly into the sludge, unable to free themselves as the weight of their own body pulled them deeper. If the planet's surface has hardened over time, it might resemble a landscape of graphite, the same material found in pencils but on an immense scale. Walking across such a surface would be treacherous. Sharp, brittle formations could snap underfoot, sending jagged shards flying in all directions. Each step could kick up clouds of fine carbon dust, filling the air with a choking, suffocating haze. Breathing would be impossible without protection, as the lungs would quickly fill with microscopic particles, coating the respiratory system in a layer of soot. But the most dangerous aspect of a carbon planet might be the sheer pressure beneath its surface. Over millions of years, the intense weight of the upper layers could have compressed carbon into solid diamond. In theory, entire continents could be made of pure diamond, locked beneath layers of hardened graphite. Diamond is one of the hardest materials known, which means that if the surface ever cracked due to seismic activity, the resulting fractures could be sharp enough to slice through metal. Anyone caught in such an event could be torn apart by razor-thin diamond shards shooting through the air at high speeds. Even if the surface remained stable, the sheer density of a diamond-rich crust would make excavation or shelter construction nearly impossible. Unlike softer rock, diamond does not erode easily, meaning natural caves or protective overhangs would be rare. There would be nowhere to hide from the elements, no way to dig into the ground for safety. The atmosphere of a carbon planet would likely be thick with toxic gases, composed of compounds like carbon monoxide, methane, and possibly hydrogen cyanide. Carbon monoxide would bind to red blood cells, cutting off oxygen supply and leading to suffocation. Hydrogen cyanide, even in small amounts, would disrupt cellular respiration, shutting down the body's ability to produce energy. The air would be a silent killer, offering no warning before unconsciousness set in. If the planet formed close to its star, temperatures could soar high enough to liquefy tar-like hydrocarbons on the surface, creating vast boiling lakes of molten carbon compounds. The air above these lakes would be thick with volatile fumes, capable of igniting with the slightest spark. A single electrical discharge, perhaps from a storm or even static buildup from movement, could trigger an explosion, turning entire regions into firestorms. Carbon-rich atmospheres might generate powerful winds, lifting fine graphite particles into the sky and creating storms that darken the landscape for days or weeks. These storms would not only reduce visibility to near zero, but would also carry abrasive particles that could wear away at anything exposed to them. Over time, protective suits, equipment, and even spacecraft could become damaged by the relentless bombardment of carbon dust. If liquid hydrocarbons exist beneath the surface, they could be released in explosive geysers, sending jets of thick, burning material high into the air. Unlike water-based geysers on Earth, these eruptions could ignite on contact with oxygen, creating pillars of fire stretching for miles. Any explorer caught in such an event would have no chance of escape, their suit melting away in seconds before being consumed by the inferno. If a carbon planet formed far from its star, it could be a frigid wasteland instead, where tar and hydrocarbons have frozen solid, forming vast plains of unbreakable black ice. In such a place, movement would be difficult, and any exposed liquid could turn to solid matter instantly. The atmosphere might be thick with freezing methane fog, further obscuring the landscape and making navigation nearly impossible. If a human were to perish on a carbon planet, their body might become part of the landscape itself. The intense conditions could prevent decomposition, leaving them frozen in time, their remains preserved beneath layers of tar and soot. Over millions of years, geological processes might even transform their body at the atomic level, turning organic material into graphite, or given enough pressure, even a small fragment of diamond buried deep beneath the surface. Any attempt to colonize a carbon planet would be an impossible task. The lack of breathable air, the hazardous surface, and the extreme conditions would make long-term survival unattainable. There would be no liquid water, no fertile soil, and no way to grow food. The energy required to sustain even a small outpost would be astronomical, with every resource needing to be transported from elsewhere. Crafting artificial sanctuaries, engineering havens on hostile worlds. No human body can naturally withstand the extreme environments of distant planets, moons, or deep space voids, but technology can bridge the gap. Engineering solutions must be developed to protect against radiation, extreme temperatures, crushing pressures, and the lack of breathable air. If humans are to extend their reach beyond Earth, they must first learn how to build safe havens in the most hostile corners of the universe. The most immediate need for artificial sanctuaries is shielding. Unlike Earth, which has a thick atmosphere and a magnetic field to block harmful cosmic radiation, most places in space offer no such protection. Any habitat on the Moon, Mars, or an asteroid will be bombarded by radiation from the Sun and deep space. Engineers have proposed various ways to counter this. One solution is using thick shielding made from local materials. On the Moon or Mars, for instance, regolith, the loose rock and dust covering the surface, could be piled onto structures to absorb radiation. Other proposals involve building underground, where several meters of rock could provide a natural barrier against radiation exposure. Pressurization is another fundamental challenge. Earth's atmosphere applies a steady pressure to human bodies, keeping fluids and gases in balance. Without it, blood would start to boil at surprisingly low temperatures, and oxygen would escape from the lungs in an instant. Any artificial sanctuary must be airtight and capable of maintaining a stable pressure inside. Inflatable habitats, designed to be lightweight but expandable, have been considered as an option for early settlements on the Moon and Mars. These structures could be deployed rapidly, then reinforced with additional shielding or support materials to keep them stable. Temperature regulation is just as critical. Many locations in space experience wild temperature swings between extreme heat and bitter cold. The Moon, for example, sees temperatures that range from 127 degrees Celsius in sunlight to minus 173 degrees Celsius in darkness. Mars, although farther from the Sun, also experiences severe cold, often dropping below minus 73 degrees Celsius at night. Habitats must be designed with advanced thermal insulation to prevent dangerous temperature fluctuations. Some designs incorporate reflective outer layers to deflect excess heat during the day, while using heat-absorbing materials to retain warmth at night. Energy supply is another major concern. Unlike Earth, where power can be easily generated using fossil fuels, hydroelectric dams, or wind farms, artificial sanctuaries must rely on alternative energy sources. Solar power is a promising option for habitats on the Moon and Mars, as sunlight is available for extended periods. However, solar panels must be built to withstand harsh conditions, such as dust storms on Mars or micrometeorite impacts on the Moon. For locations where sunlight is limited, such as deep space stations or bases on Jupiter's icy moons, nuclear reactors could provide a steady energy source, ensuring that life support systems remain active even when solar energy is unavailable. Artificial gravity is another challenge that must be addressed. Prolonged exposure to low or zero gravity has been shown to cause muscle atrophy, bone loss, and other health complications. On the Moon and Mars, gravity is weaker than on Earth, and in deep space, there is no natural gravity at all. Some proposed space stations, such as the classic rotating wheel design, would use centrifugal force to simulate gravity. By spinning at a calculated speed, such a station could create a stable environment where humans could walk, exercise, and live without the harmful effects of weightlessness. Beyond the technical aspects of survival, artificial sanctuaries must also provide environments that support human well-being. Psychological factors play a huge role in long-term space missions. Small, enclosed spaces with limited social interaction and no natural scenery can lead to mental health challenges such as stress, depression, or cabin fever. Engineers are exploring ways to make artificial sanctuaries feel more like home. Some concepts include smart walls that can change color or display artificial landscapes to mimic the feeling of being on Earth. Others propose using hydroponic gardens inside habitats, not only to grow food, but also to provide a natural, calming atmosphere. One of the most intriguing ideas for artificial sanctuaries is terraforming, modifying entire planets or moons to make them more Earth-like. While true terraforming remains a distant possibility, smaller-scale approaches could be applied in controlled environments. Some proposals suggest creating enclosed domes with their own self-sustaining ecosystems, complete with breathable air, natural water cycles, and plant life. Such a system would require careful balance, as every element, from oxygen production to waste recycling, would need to function in harmony to maintain stability. For survival in space, redundancy is key. Artificial sanctuaries must be built with backup systems for every critical function. If an oxygen generator fails, there must be an alternative supply. If one power source is lost, another must be available. This principle applies not only to space stations, but also to planetary bases and deep space vessels. Engineers must design these structures with multiple fail-safes to ensure that no single failure results in disaster. Bioengineering for survival, adapting to the universe's brutal extremes. Survival beyond Earth is a challenge that extends beyond spacecraft, suits, and technology. The human body itself is not built for the vast and brutal conditions of space, let alone the extreme environments found on alien worlds. Radiation, low gravity, toxic atmospheres, and crushing pressures all work against the fragile biology of Homo sapiens. While engineering solutions like reinforced habitats and protective suits can help, there is another possibility, one that reaches down to the very building blocks of life. If humans are to live among the stars, they may need to alter themselves at a fundamental level. Bioengineering, the modification of human biology, could be the key to survival in the most extreme places in the universe. The human body has evolved to survive in one specific environment, Earth. Even small changes in temperature, pressure, or oxygen levels can push it past its limits. The concept of modifying humans to withstand different planetary conditions is not new, but advances in genetics, synthetic biology, and biotechnology are bringing it closer to reality. These modifications could take many forms, from genetic enhancements to artificial organs designed for alien environments. Radiation is one of the greatest threats to human survival in space. Cosmic rays and solar radiation can penetrate spacecraft and spacesuits, damaging DNA and increasing the risk of cancer, organ failure, and neurological damage. On Mars, for example, the thin atmosphere provides little protection from high-energy particles that constantly bombard the surface. One potential bioengineering solution is the introduction of genes from radiation-resistant organisms, such as Deinococcus radiodurans, a bacterium capable of surviving extreme radiation exposure. By incorporating similar DNA repair mechanisms into human cells, scientists could create a body more resilient to radiation, reducing the risk of long-term genetic damage. Another possible adaptation involves melanin, the pigment responsible for skin color in humans. Certain fungi, like those found in the irradiated ruins of Chernobyl, use melanin to convert radiation into energy, protecting themselves from harm. If humans could develop a similar adaptation, they might be able to tolerate higher radiation levels without the need for heavy shielding. This could be particularly useful for long-duration missions on the Moon or Mars, where protection from cosmic rays is a major challenge. Low gravity presents a different set of problems. Astronauts who spend months aboard the International Space Station undergo strict exercise routines to counteract these effects. But in the long run, living in space or on low-gravity planets may require more than just workouts. One potential solution is genetic modification to increase the production of myostatin inhibitors, proteins that promote muscle growth and density. This could help prevent muscle loss and maintain physical strength in environments with weaker gravitational pull. Bone density is another major concern. On Earth, bones remain strong due to the constant force of gravity acting on them. In microgravity, bones begin to lose calcium, making them weaker and more prone to fractures. Some animals, such as certain species of bears, can hibernate for months without suffering bone loss. Scientists are studying the genetic mechanisms behind this phenomenon and exploring ways to apply it to humans. By mimicking the biological pathways that preserve bone density in these animals, it may be possible to prevent bone deterioration in space travelers. Breathing in alien atmospheres is another obstacle to survival. Earth's air contains 21% oxygen, a level necessary for human life. But many exoplanets may have atmospheres rich in carbon dioxide, methane, or other gases that are toxic to us. Some organisms on Earth, such as extremophiles, have adapted to environments with little to no oxygen, using alternative metabolic pathways to extract energy. If similar biological mechanisms could be incorporated into human physiology, it might allow for survival in places that would otherwise be completely inhospitable. One idea involves modifying hemoglobin, the protein in red blood cells that carries oxygen. Some deep-diving mammals, such as whales and seals, have hemoglobin variants that bind to oxygen more efficiently, allowing them to hold their breath for extended periods. If humans were equipped with a similar adaptation, they might be able to survive with much lower oxygen levels, reducing their dependence on external life support in thin or altered atmospheres. Many planets and moons experience extreme temperature swings, from searing heat to deep, freezing cold. Some animals on Earth have developed remarkable adaptations to withstand such extremes. The wood frog, for instance, can survive being frozen solid by producing cryoprotectants, natural antifreeze chemicals that prevent ice crystals from forming in its cells. If humans could harness similar mechanisms, they might be able to tolerate extreme cold without suffering frostbite or cellular damage. At the other end of the spectrum, desert-dwelling animals like the oryx have developed ways to keep their bodies cool, even in scorching temperatures. By adjusting blood flow and water retention, they can survive in conditions that would cause severe dehydration in humans. Understanding and replicating such adaptations could provide a way for humans to endure the intense heat found on some exoplanets or in extreme environments like Venus's upper atmosphere. A radical idea involves the possibility of artificial symbiosis, introducing helpful microorganisms into the human body to assist with survival in extreme conditions. Some deep-sea creatures rely on bacteria that help them process toxic chemicals into usable energy. If a similar relationship could be engineered for humans, it might allow for new metabolic abilities, such as extracting nutrients from otherwise indigestible materials or breaking down harmful substances in alien environments. Some tardigrades, microscopic organisms known for their resilience, can survive extreme radiation, dehydration, and even the vacuum of space. They achieve this by producing unique proteins that protect their cellular structures. If scientists could incorporate tardigrade-like proteins into human cells, it might make people far more resistant to the harsh conditions of space, potentially even allowing for survival outside of protective habitats for short periods. Of course, bioengineering for space survival is not without ethical and practical concerns. Modifying the human body at a genetic level carries risks, and unintended consequences could arise. Changes made for one environment might not be reversible, leading to potential difficulties if conditions change. Social and moral questions also come into play. Should humans fundamentally alter themselves to fit the universe, or should they instead rely on technology to create Earth-like environments wherever they go? Research in genetic modification, synthetic biology, and biotechnology is advancing rapidly. If humanity ever hopes to become an interstellar species, adaptation may not be a choice, it may be a necessity. Future space travelers might not only wear protective suits, but also carry within them the genetic and biological tools needed to survive. Chimeric evolution, blending Earth and alien genomes for ultimate resilience. If extraterrestrial life exists and possesses unique biological traits, could those traits be integrated into human biology to create a species capable of thriving in conditions no Earth-born organism ever could? The concept of chimeric evolution, the blending of genetic material from different species, already exists on Earth. Scientists have successfully introduced jellyfish genes into mice to make them glow, inserted bacterial DNA into crops for pest resistance, and even modified human cells with animal genes to study diseases. Would extraterrestrial DNA, assuming it even exists in a comparable form, be compatible with human biology? Could its sequences be translated into something functional within our own cellular machinery? One of the most extreme environments for life on Earth is the deep ocean, where pressures are immense, sunlight is non-existent, and temperatures are near freezing. Yet, deep-sea organisms have evolved to survive using mechanisms unknown to surface life. Some bacteria and archaea, for instance, can withstand radiation levels that would be fatal to humans. If similar organisms exist on alien worlds, their genetic blueprints could hold the key to making humans more resilient to cosmic radiation, a major obstacle to long-term space travel. Many planets and moons in our solar system have little to no breathable air. Deep-sea fish and some high-altitude animals on Earth have developed specialized proteins that allow them to extract more oxygen from their environment or survive with extremely low levels. Could future humans be enhanced with similar traits, perhaps integrating the hemoglobin adaptations of bar-headed geese, birds that can fly over the Himalayas where oxygen is scarce? Or could we go even further, incorporating traits from alien microbes that rely on entirely different biochemical processes, such as extracting energy from sulfur or methane instead of oxygen? Even more speculative is the idea of blending human DNA with entirely alien forms of life, assuming we ever discover extraterrestrial organisms with radically different biochemistry. Earth's biology is carbon-based, using water as a solvent, and relying on DNA and RNA to encode genetic information. But in the vastness of the universe, there may be life forms that use alternative biochemistries, such as silicon-based life or ammonia-based metabolisms. If such life exists and is capable of genetic exchange, it could lead to possibilities beyond anything currently imaginable. Could a human-alien hybrid organism process toxic atmospheres, endure extreme gravity, or survive on planets without traditional food sources? Many animals on Earth experience the world in ways we cannot. Mantis shrimp can see an extended spectrum of colors beyond human vision. Birds can sense Earth's magnetic field, and some insects communicate using ultraviolet patterns invisible to us. If alien species had evolved with entirely new ways of perceiving their surroundings, integrating those abilities into human biology could open up new sensory experiences. Future astronauts engineered with enhanced vision might see radiation directly, detect chemical changes in the air, or even process time differently under conditions of extreme gravity or acceleration. Quantum biology in cosmic environments, unveiling hidden survival mechanisms. In recent years, researchers have begun uncovering surprising ways in which quantum mechanics may influence biological systems. Unlike large-scale survival strategies such as building habitats or terraforming planets, quantum biology explores resilience at the microscopic level, revealing hidden mechanisms that could make life more adaptable than previously imagined. One of the most well-known examples of quantum biology on Earth is photosynthesis. Plants, algae, and some bacteria use sunlight to produce energy, but they do so with a level of efficiency that defies classical explanations. When a photon, a particle of light, enters a plant cell, it needs to transfer its energy to a reaction center where chemical processes can convert it into usable energy. Classical physics would suggest that the photon's energy moves randomly, taking multiple inefficient pathways before reaching its destination. Instead, quantum mechanics suggests that the energy follows multiple paths simultaneously, selecting the most efficient route in a process known as quantum coherence. If such a process exists on Earth, it raises an interesting question. Could alien life forms on distant exoplanets have evolved similar or even more advanced quantum adaptations? Some researchers believe that quantum tunneling, a phenomenon in which particles pass through energy barriers that should be impassable, may play a role in biological processes as well. Enzymes, the tiny molecular machines that drive biochemical reactions, might use quantum tunneling to accelerate reactions beyond what classical physics would allow. This ability could be particularly advantageous for life in extreme environments, such as the frigid ice-covered oceans of Europa, or the toxic clouds of Venus, where standard biochemical reactions might be too slow to sustain life. If organisms on these worlds have evolved to exploit quantum effects, they may be capable of surviving in conditions previously thought impossible. Another fascinating quantum effect is entanglement, in which two particles become so closely linked that a change in one instantly affects the other, even across vast distances. While this phenomenon is still being explored in biological systems, some scientists speculate that it could play a role in processes such as navigation. Migratory birds, for example, seem to use Earth's magnetic field to guide their journeys, a feat that might involve quantum entanglement within proteins in their eyes. If quantum-based navigation exists on Earth, it could open the door to entirely new ways of sensing the environment. Could alien organisms use quantum entanglement to detect magnetic fields on distant planets or even across interstellar space? Could advanced civilizations harness quantum effects for survival in ways we have yet to comprehend? Traditional biology suggests that life requires stable conditions, a solvent like water, and a steady energy source. However, if quantum effects play a more significant role in biology than currently understood, life might emerge in ways that defy traditional expectations. Could organisms exist in the freezing depths of rogue planets, harnessing quantum effects to sustain biochemical reactions in the absence of sunlight? Could extremophiles on distant worlds use quantum coherence to extract energy from unlikely sources, such as weak electromagnetic fields or the decay of radioactive materials? If life can manipulate quantum effects to enhance its survival, then the possibilities for extraterrestrial life become even broader. It may mean that the boundaries of habitability extend not just to planets in the so-called Goldilocks zone, but also to seemingly inhospitable worlds with extreme radiation, cold, or chemical conditions. Adaptive pigmentation. How color shifts could shield life from intense radiation. On Earth, color is often associated with camouflage, communication, or attracting mates. But in space, pigmentation could serve a different, far more critical role, shielding life from deadly radiation. Whether through natural evolution or bioengineering, organisms exposed to intense ultraviolet, X-ray, or cosmic radiation might develop adaptive pigmentation to survive. Some could darken their skin, shells, or exoskeletons to absorb and dissipate harmful energy, while others might shift colors in real time, adjusting to fluctuating radiation levels in alien environments. Melanin plays a crucial role in protecting cells from ultraviolet radiation. People with darker skin tones have more melanin, which helps absorb and dissipate UV rays, reducing the risk of DNA damage. Certain fungi found inside the damaged reactors of Chernobyl appear to thrive in high radiation environments, using melanin to convert radiation into chemical energy. This process, called radiosynthesis, suggests that some life forms might not only survive, but even harness radiation for metabolic purposes. On an exoplanet orbiting a highly active star, for example, life forms might develop an automatic response to sudden bursts of radiation. When radiation levels spike, their skin, scales, or outer layers could darken, forming a protective barrier. When conditions are safer, they could revert to a lighter color, reducing heat absorption and conserving energy. This type of adaptation would be similar to how some Earth animals change color for temperature control, like chameleons and certain cephalopods that adjust their skin tones in response to environmental changes. Mars provides a possible testing ground for such adaptations. The planet's thin atmosphere does little to block harmful radiation, making the surface a dangerous place for unprotected organisms. Any life that might exist underground could potentially evolve pigmentation defenses if exposed to surface conditions over time. Future Mars colonists might also need to consider this adaptation. If human settlements rely on domes or artificial structures with some exposure to natural sunlight, individuals with darker skin or increased melanin production could have a slight advantage in radiation resistance. In the long term, genetic engineering might allow humans to enhance their own melanin production or even develop new, more effective pigments for radiation shielding. Carotenoids, found in plants, algae, and some bacteria, help protect against oxidative stress caused by radiation exposure. These pigments are responsible for the red, orange, and yellow colors of many fruits and vegetables. They act as antioxidants, neutralizing harmful molecules that form when cells are exposed to high-energy radiation. If life on a distant planet evolved under extreme radiation conditions, it might develop carotenoid-based pigments to minimize cellular damage. A similar strategy could be applied in synthetic biology, where organisms are engineered to produce high levels of protective pigments for space travel or off-world colonization. Another potential radiation-shielding pigment is bacteriorhodopsin, a protein found in certain microorganisms that live in extreme environments on Earth. This molecule is responsible for capturing light energy and has been found in some of the most inhospitable places on the planet, such as hypersaline lakes and deep-sea vents. In high radiation environments, a modified version of this pigment could act as a biological barrier, absorbing and reflecting harmful wavelengths of light. If introduced into human cells or artificial biosystems, it could help shield space travelers or extraterrestrial colonists from radiation damage. Some exoplanets may already be home to life forms that have developed extreme pigmentation to cope with intense radiation from their host stars. Planets orbiting red dwarfs, for example, receive frequent bursts of high-energy radiation due to stellar flares. Any surface-dwelling organisms on such worlds might evolve deep black or reflective silver coatings to minimize radiation exposure. If they rely on photosynthesis, they might also develop unique pigments adapted to absorb only the safest wavelengths of light, avoiding the dangerous ultraviolet and X-ray emissions of their sun. Bioengineers could develop materials infused with biological pigments, creating smart fabrics that change color in response to radiation levels. These materials could be used in spacesuits, habitats, or even spacecraft coatings to provide an extra layer of protection against cosmic rays. This approach would combine biological adaptation with technology, creating hybrid solutions that mimic the resilience of living organisms. Some researchers are studying how melanin-rich fungi could be used to create self-repairing radiation shields for spacecraft. Others are investigating the potential of algae-based coatings that absorb harmful radiation while producing oxygen for closed-loop life support systems. These experiments suggest that biological solutions may offer a more flexible and efficient way to protect against space radiation than traditional shielding methods like lead or water barriers. As humanity pushes further into space, the ability to adapt to high radiation environments will become increasingly important. Whether through natural selection, synthetic biology, or direct genetic engineering, the development of adaptive pigmentation could be a critical factor in ensuring survival on other worlds. Bioadaptive architecture, designing habitats inspired by extraterrestrial life forms. One of the most promising approaches to designing future space habitats is to look at how life itself has adapted to harsh conditions. These biological solutions offer a blueprint for engineering habitats that are not only functional but also capable of adapting and evolving alongside the needs of their inhabitants. Many of nature's strongest structures are built using lightweight yet highly durable materials. Consider the hexagonal honeycombs of bees, the silica shells of diatoms, or the layered structures of mollusk shells. These designs maximize strength while minimizing weight, a principle that is essential in space construction, where every gram counts. If future habitats could mimic the self-assembling properties of these structures, they could reduce the need for heavy raw materials and instead form their own frameworks using local resources. A base on the Moon or Mars, for example, might use bio-inspired materials that harden when exposed to the environment, much like how corals form reefs by extracting minerals from seawater. Some Earth organisms also create living structures that grow and repair themselves. Mycelium, the root-like structure of fungi, spreads underground and can form networks that are strong, flexible, and self-healing. Researchers are already experimenting with mycelium-based materials that could be used to 3D print shelters on other planets. A habitat built from such a material wouldn't just be a passive structure. It could expand, adapt, and even regenerate if damaged. If cracks formed in the walls due to temperature fluctuations or small meteorite impacts, the material could fill in the gaps on its own, much like how a tree heals after a branch is cut. Certain desert plants have reflective surfaces that deflect sunlight, while deep-sea creatures produce bioluminescent coatings to camouflage themselves. A space habitat might incorporate similar principles using materials that can automatically adjust their reflectivity depending on exposure to solar radiation. While we may not be able to create self-repairing human DNA just yet, we could design habitat walls that incorporate radiation-resistant compounds or self-healing nanomaterials that mimic these biological defenses. Many plants and microbes purify water by breaking down toxins and absorbing pollutants. On Earth, wetlands act as nature's water treatment facilities, filtering out contaminants and cycling nutrients back into the environment. If space habitats used bio-inspired water systems, they could recycle waste efficiently, reducing the need for constant resupply missions. Bioengineered algae or bacteria might be used in filtration walls, constantly processing air and water to keep the living environment stable. Some of the most extreme environments on Earth are home to organisms that rely on each other for survival. In deep-sea hydrothermal vents, tube worms and bacteria work together to process chemicals from the ocean floor, creating a stable system that supports a variety of life. If a space habitat could incorporate a similar living ecosystem, it could provide long-term sustainability. Perhaps walls lined with beneficial microbes could absorb carbon dioxide and produce oxygen, or engineered plants could produce both food and structural materials. Some of the most fascinating inspirations for bioadaptive architecture come from the way life forms protect themselves from impacts. The mantis shrimp, for example, has an ultra-tough club-like appendage that can break through aquarium glass. Yet it remains undamaged due to its unique micro-layered structure. If habitat walls were designed with similar multi-layered materials, they could absorb impacts from space debris or micrometeorites without cracking. Many animals and insects build burrows to shield themselves from extreme temperatures and predators. If future Mars colonies were built beneath the surface, they could use the planet's own soil as insulation against radiation and temperature shifts. Lava tubes, natural tunnels formed by ancient volcanic activity, might serve as pre-existing shelters that could be reinforced using bio-inspired materials. Beyond structural adaptations, the way organisms regulate their energy and resources could also influence habitat design. Desert animals conserve water through highly efficient metabolic processes, reducing waste and maximizing hydration. A future lunar or Martian habitat might employ similar strategies, with systems designed to capture, purify, and recycle every drop of water and every breath of air. Waste might not be seen as something to dispose of, but as a resource that can be reprocessed into fuel, building material, or nutrients. As artificial intelligence and biotechnology advance, space habitats could become even more adaptive. Instead of being static, lifeless structures, they might be able to sense and respond to their surroundings, much like a living organism does. Walls could change their porosity to regulate air circulation. Structures could shift their shape to optimize heat distribution, and living materials could slowly alter their composition to withstand new environmental challenges. Some researchers even propose the idea of fully biological habitats, structures that are not just inspired by life, but are, in a way, alive themselves. These habitats could be grown rather than built, expanding as needed and regenerating when damaged. Instead of astronauts landing on Mars with prefabricated shelters, they might bring bioengineered spores that grow into sturdy, airtight domes. Such an approach could drastically reduce the amount of material needed for long-term space missions, making colonization more practical and sustainable. Experiments with bioconcrete, which heals itself using bacteria, and living root bridges in India, which naturally strengthen over time, show that nature provides some of the best solutions for building in extreme conditions. If these ideas are applied to space exploration, the first permanent settlements on other planets might not be made of cold metal and glass, but of materials that breathe, grow, and evolve to meet the challenges of the cosmos. Radical regeneration, learning from alien species that rewrite mortality. Regeneration has often been seen as an anomaly, limited to a few organisms. However, more recent discoveries have shown just how widespread this ability is in nature, especially in some of Earth's most unusual and resilient species. For instance, certain species of salamanders, like the axolotl, can regrow entire limbs, spinal cords, heart tissue, and even parts of their brains. This regenerative power goes far beyond what is possible in humans, where healing is typically limited to scar tissue formation and the repair of only certain tissues. Similarly, some species of flatworms called planarians have the astonishing ability to regenerate lost parts of their bodies, sometimes even entire organisms, after being severed in half. Planarians can essentially turn a small fragment of their body into an entirely new, functional organism. This process has been studied extensively by biologists and has led to the discovery of key biological mechanisms involved in regeneration, such as the role of stem cells in tissue repair. The regenerative abilities of these creatures seem to rewrite the rulebook on mortality, offering an entirely different approach to dealing with injury, decay, and aging. In environments where injury is inevitable, whether due to harsh conditions, hostile environments, or the stresses of living in space, species that can quickly and effectively repair their bodies might have a distinct advantage. Imagine encountering a life form on an alien planet that has mastered the art of regenerating its tissues, organs, or even entire limbs in a matter of days. The survival advantages of such abilities would be immense, making these creatures well suited to environments where injury or damage might otherwise be fatal. The mechanisms behind radical regeneration in Earth's species are diverse and not yet fully understood, but they offer clues to how organisms might repair their bodies. In the case of the axolotl, for example, when the animal loses a limb, specialized cells at the site of the injury begin to transform into a type of stem cell known as a blastema. These stem cells proliferate, differentiate, and develop into the various tissues necessary to rebuild the lost limb, such as muscle, bone, and skin. What's more astonishing is that this process doesn't leave behind any scars. A remarkable feat for a species that can regrow an entire body part. Scientists are studying how stem cells in humans could be harnessed to treat injuries, regenerate damaged organs, or even reverse the effects of aging. If humans could tap into the regenerative potential of their own cells, it could revolutionize healthcare, allowing people to heal from injuries that would currently be impossible to recover from, such as spinal cord damage or heart disease. The hope is that by understanding how animals like the axolotl regenerate, scientists might be able to replicate these processes in humans, creating new avenues for medical treatment. Space exploration could provide an ideal environment to test the limits of biological regeneration. If humans or future explorers were able to modify their bodies to regenerate lost tissues, It could eliminate the need for complex surgeries and medical interventions. Imagine a situation where an astronaut suffers an injury, say a deep cut or a broken bone, but instead of needing immediate medical treatment, their body simply begins to repair itself, regenerating tissue and restoring full functionality. In this sense, the ability to regenerate could be the ultimate survival tool for humans, helping to mitigate the risks of working and living in extreme, unfamiliar environments. Biocybernetic fusion, integrating organic biology with advanced technology. The idea of merging biology with technology draws inspiration from the rapidly advancing fields of prosthetics, cybernetics, and biotechnology. In the modern world, we already see rudimentary examples of biocybernetic fusion, bionic limbs controlled by the brain, implants that help people hear or see, and even pacemakers that regulate the heart. These technologies have already improved the quality of life for many individuals. In the most extreme environments, humans face challenges that go beyond the limits of the biological body. The human body is fragile and vulnerable to many dangers in space. The very survival of humans in space may one day depend on the integration of advanced technology with our biological systems, creating a new class of organisms, part human and part machine, capable of withstanding these extreme conditions. Imagine a person who, instead of wearing a bulky spacesuit, has embedded technological components into their body that allow them to breathe in an airless environment, resist extreme temperatures, and even withstand high levels of radiation. These embedded systems could monitor the body's vital functions, providing real-time data to prevent overexposure to harmful conditions. For example, tiny sensors integrated into the skin could detect harmful levels of radiation and activate a shielding mechanism to protect the body. This would eliminate the need for external protection and allow the individual to adapt to various environmental factors without being confined to a spacesuit or protective habitat. Advanced prosthetics like robotic limbs or exoskeletons could be developed to provide strength and mobility in environments that would be unbearable for unmodified humans. Imagine astronauts on Mars, where gravity is weaker than on Earth, but the atmospheric pressure is too low to support normal biological functions. Through biocybernetic fusion, these astronauts could have artificial limbs that help them move more efficiently in the Martian environment, while their body would be able to compensate for the weak gravity, supporting muscle function through robotic assistance. The integration of advanced cybernetic eyes or sensory organs might allow a person to see beyond the visible spectrum, detecting radiation, heat sources, or even electromagnetic fields that would otherwise be invisible to the human eye. By augmenting our natural senses with technological enhancements, astronauts could navigate and interact with their surroundings in radically new ways. Biocybernetic fusion could enhance human healing abilities. Imagine a system in which nanobots are deployed inside the body, repairing tissue at the cellular level and enhancing the body's natural healing mechanisms. These nanobots could work alongside bioengineered tissues that regenerate quickly, providing a rapid response to injury or illness. With such biocybernetic systems in place, the chances of survival would increase significantly. As we merge our biology with technology, we may not just be enhancing our ability to live in extreme environments, but also reshaping what it means to be human. The line between biology and technology could blur, creating beings that are no longer bound by the limitations of their organic bodies. This fusion could unlock new forms of human expression, perception, and even cognition. Just as a computer can store vast amounts of information and process complex tasks, biocybernetic enhancements could enable humans to do the same, allowing for cognitive abilities that far exceed our natural limits. Imagine a mind augmented with vast databases of information, allowing humans to process data, communicate, and interact in ways that are impossible today. This potential brings both hope and concern. On the one hand, biocybernetic fusion could unlock the full potential of human beings, making it possible for us to live in space, explore distant worlds, and even extend our lives. On the other hand, it raises questions about the nature of humanity and the boundaries of technological intervention. At what point do we stop being human and become something else entirely? How much of our biological identity should we be willing to sacrifice in the pursuit of survival? These questions will become increasingly important as technology continues to advance and as we explore the possibilities of merging biology with machines. What other methods could humans use to overcome the multitude of dangers inherent in traveling beyond our pale blue dot? Comment down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.